Yogesh has made arrangements for things to be mostly streamed. Thanks for coming all the way. A lot of people have come from abroad. Many of you, even from India, would have come to IUCAA for the first time, and we're taking this opportunity to welcome you to this institute. I thought I'd just quickly introduce IUCAA to you in case you have not been here before. We are 31 years old, and we've been around from the very beginning. We had a very keen interest in solar physics, though it forms a small part of our activities. IUCAA was set up in the 80s as part of a drive by the Indian government to make universities research active. Very, very curious origin of the Indian university system. Most universities were not set up to be research active. They were glorified teaching schools. In the 80s, the government realized that the universities were missing a very big chunk of academic activities in which students could get involved in research along with their teachers. And it was felt that for some subjects, it is very difficult to make the 700 universities at that time in India research active. And so some of these inter-university centers were set up, and one of them was in astronomy astrophysics, set up here, such that people from the Indian universities could come. These are faculty as well as students to come and do their research in astrophysics. The unusual thing about solar physics and astrophysics in general is that it is not a subject that is taught in universities, and so one of our mandates is to make sure that universities teach astronomy, astrophysics, and this is why this is what we've done in the last 3 decades. Now a lot of universities are active in teaching astrophysics related subjects in various departments, and this is rapidly increasing now that the university system has been liberalized, and there are a lot more choice. There's a lot more choice than there was. That is one of the reasons you'll see a lot of people from Indian universities here today, because we use these opportunities to make sure that people from universities can come and interact with the international crowd, as well as people from other institutes in India. But as a result of our being kind of the nodal institute for universities, it's also meant that as India has moved into an era of global cooperation in science in general and astronomy in particular, we have become stakeholders in some of the biggest projects that are going on in India and the world. So we are one of the nodal institutions, for example, that is empowered to set up the third LIGO observatory in India. The work is starting off very nearby here. And then we are one of the institutions, along with Ares and in Institute of Astrophysics, in the building of the 30-meter telescope, along with 2 of our Asia Pacific partners, Japan and China. We also play a very important role along with our neighbors, the NCRA, in the SKA part of, and the other big thing is, of course, we are getting involved in some of the biggest projects for the Indian Space Research Organization, ISRO, which has, as you know, taken a huge initiative in getting involved in astronomical projects. We will hear quite a bit about ISRO projects in this conference, as well as the other large initiatives in solar physics that I did not talk about because this is the topic of this week. I welcome you again, and this is a wonderful time also, in addition to the fact that we continue this tradition of the Asia Pacific meeting. A good time to be in solar physics. The sun has been in the papers not because of being the sun, but also the new research that's coming out on the sun. Two people outside the field, quite a lot of late, and we are also poised from India to very soon launch Aditya L1, of which you will hear quite a bit in this meeting, and that makes it a wonderful time to bring people together. We'll also send out the message, and we're trying quite hard during this meeting to involve the media to send out the message that that we are at a good time to do solar physics, and this is a good time for India to be involved on the global scale to study the sun. Thank you very much for being here, and I hope things go well. We have a large number of public events also scheduled along with this meeting, and you'll see the general public come in for our public talks, as well as the media in those events, and I hope you enjoy the menu we have for you. This gives us an opportunity of collaborating with a large number of other institutions. Our sponsors are listed on the screen, but this is also an opportunity for us to collaborate with IUCAA Pune, the other big institution in Pune who has a pretty good activity of solar research, and some of the other institutions in India who will be represented very soon. Thank you.
Thank you so much. So the meeting is jointly organized by IUCAA and Inter-University Indian Institute of Science Education and Research, and therefore I would like to invite Professor Prasad Subramanian, who is also co-chair with me for the Scientific Organizing Committee, to say a few words and introduce ISO to you.
Good morning, welcome. So I'm from the Indian Institute of Science Education and Research, that logo with the black dot in the center and the red thing up there. So welcome to this meeting. Hope you enjoyed. Some of you were staying in our guest house. I invite you to be curious about our institute. We are a large undergraduate and postgraduate research and teaching institute. We carry out research and teaching in a wide variety of disciplines, including physics, and I'm one of the 3 astronomers there. So we're growing, and we have a vibrant student body, and so I invite you to be curious about it. About this meeting, welcome. I hope we have a productive and stimulating meeting. And I wish you all the best, and I'll be seeing you around.
Thank you, Prasad. Okay, Prasad has to go to teach his class now, but he'll be back in an hour. All right. Let me see what else I have to say before we start the meeting. Actually, I think I've covered everything. I just wanted to say that it's being organized jointly by IUCAA and IISER Pune, but we have had good generous support from other institutes, Indian Institute of Astrophysics, Center for Space Science, Center of Excellence in Space Science India, CESI, which is an institute within the IISER Kolkata, ARIES, which is in Nainital, ISRO, our space agency, and the Indian Institute of Science in Bangalore. With that, I have to make one quick announcement that all the poster boards are outside, and all the posters will be displayed all through the week, and we have dedicated poster sessions, and there are awards related to the poster session as well as the oral talks for young scientists. I just remind you, 3 years, maximum 3 years postdoctoral experience for oral talks, and the posters will be only for PhD students. So if you have not signed up for that, please do sign up to be considered if you like by lunchtime today, so that our committee member would not have to then keep adding, so they can start judging posters and talks objectively. With that, I welcome you all again, and I hope that we will have a fruitful week. Thank you very much. I need to invite Venkat for chairing the session. The laptop is restarting. What happened? Okay. So there are 5 minutes and 3 minutes. While this is being set up, I'll just say that the program has been quite dynamically changing because of all these cancellations. So the one you have in your pack is not the final one. So if you want to get the final program, please have a look on the web page, and it's all scheduled. And I hope that there won't be any changes anymore with that. Thank you. Venkat. Yeah, so you will be chairing till lunch. So that is,
So good morning, everybody. Without much ado, I will invite Shankar to give his first talk. I think he has 30 minutes, in which we have eaten into 5 minutes have gone, but you will have your 30 minutes. It's okay. I mean, we'll have a relaxed thing. And I will warn you maybe at 10 minutes or 5 minutes. Okay.
So I'm just going to talk about Aditya. Before that, let me thank the organizers and IUCAA for inviting me to give this talk on Aditya. So this is a first Indian dedicated solar observatory to be placed at the L1 Lagrangian 1 point. And as the picture depicts here, this covers the major science objective of this mission is to study the chromospheric and coronal dynamics, including solar flares and CMEs, and also the particle propagations in the interplanetary medium. And so there's 4 remote sensing instruments and 3 in situ instruments on board this Aditya L1 mission. 30 minutes is very short to cover the whole thing. So what I'm going to give you a brief of the science which we are expected to do with this mission, and also some of the instrument capabilities, because many of the science you can't achieve it without the instrument performance. So this gives you a feel for what is the satellite and how the payloads are arranged on the satellite. It's a multi-institute and research organization involvement in this whole observatory. And IUCAA themselves is making one payload on board Aditya. Many institutes lead the payload development, and ISRO to provide the satellite and launch. And ISRO also does develop a lot of technology for these payloads. Most of the optics and detector electronics are developed by ISRO for these payloads. And ISSDC, which is our data reception center at Bangalore, will support the data download and data dissemination in collaboration with the payload operations centers of each of these payload. It is now scheduled to be launched in 2020-2021 on a PSLV XL vehicle. Takes about 100 days to travel to L1 before the payload start commissioning. And as of now, there is no payload operations during the cruise phase. So during this 100 days, it's going to be a quiet period for Aditya. And it's designed for a nominal 5-year life. And we expect that it will last longer than the 5 years. This is the consolidated science goals of Aditya. So mostly it covers the diagnostics and dynamics of the chromospheric and coronal structures on the sun. And it also has this measurements of coronal magnetic topology and field measurements. This will be the first time we will be able to do coronal field measurements, direct measurements in the corona using the infrared line at 10747 angstrom. And you also see some of the instruments which will talk about the coronal abundances and the first ionization potential effects studies, and talk about particle acceleration mechanisms, prominence studies, and sun climate relations. So the two colors what you see here is the black one is the one where Aditya was initially configured for a low Earth orbit mission with a single coronagraph. But when it got upgraded to a observatory class mission with multiple payloads and being put at L1, these are the science goals which have been added to enhance the science capabilities of Aditya L1. This gives you a feel for the stored view and then the solar panel opened view, and also the placements of the instruments on the satellite. You see the two gigantic instruments. One is the visible emission line coronagraph, which is the coronagraph which operates from 1.05 to 3 solar radii to do both CME studies as well as the loop dynamic studies. It's mainly built by Indian Institute of Astrophysics, Bengaluru. And the next one is the Solar Ultraviolet Imaging Telescope being built here at IUCAA. This looks at the UV band, near UV band from 200 to 400 nanometer. And we have two X-ray spectroscopic instrument, which acts like a sun as a star, but reasonably moderate spectral resolution and large energy range coverage. These two are built at URO Satellite Center at Bengaluru. And apart from these four remote sensing instruments, we also have three in situ instruments. One is called PAPA, Particle Analyzer Package for Aditya, which is built by Space Physics Laboratory at VSSC, Trivandrum, which is one of the ISRO centers. And there is this Aditya solar wind particle experiment built by Physical Research Laboratory in Ahmedabad. And we also have a magnetometer on boom, which is again built by URSC in Bangalore. So this magnetometer has, it has a 2 magnetometer and put it on a boom at 3 meter and 6 meter to nullify some of the satellite magnetic field generated by the satellite. This gives you an overall view of the field of view coverage as well as the capabilities of each of the payload. What you see here on the left-hand side is the field of view of the VELC. We have two different field of view. Imaging is slightly a larger field of view compared to the spectroscopic channels. And you also see the images in the center, which would come from the suit. So in combination with the VELC and suit, we will be able to cover the full range of solar photosphere, chromosphere, and corona up to 3 solar radii in the imaging, and up to 1.5 solar radii in the spectroscopic mode. And the spectroscopy also is done with multi-slit configurations in order to minimize the scanning time required to cover the full field of view. So this is about configured as a 4-slit spectroscopy. And so at a time, you will get information from these 4 different regions in the spectral channel. And it's also configured with the 3 different spectral lines, 5303, 7892, and 1.04 micron lines. So you have different temperature lines so that you can do temperature diagnostics by using the line ratio techniques. And on the right-hand side, what you see here is a coverage of the X-ray payloads, starting all the way from 1 keV to go up to 30 keV to cover both the thermal as well as the non-thermal emissions from this coronal region. And this is expected to provide higher sensitivity compared to the previous missions. And having a large energy range and reasonably good spectral resolution, it can also do some of the abundance studies of the coronal regions. So I'll come to few examples of what its capabilities in the future slides. Oops. Sorry. Okay, these are the remote sensing payloads. It basically covers both the solar wind particle as well as the strahl particles coming from the sun, covering the energies from few tens of eV to all the way up to something like 20 MeV per nucleon. This would allow us to study the particles coming from the sun, both during the quiet as well as the active period. And along with the particle monitors, we also have a magnetometer, which would cover the three-dimensional vector magnetic field measurements of the in situ magnetic region. So that covers mostly the dynamics which is happening on the sun and what it is throwing into the interplanetary medium, and you do sample them at the L1 point. So it acts like a kind of a space weather instruments. And ISRO is trying to capitalize on this to see what level we can get into the space weather aspects of the whole payloads. So I'll just give you brief about the science capabilities of each of the payloads and also the uniqueness of these payloads, which gives us this advantage of doing the science. And as I already told you, it covers the dynamics of the coronal regions, the visible VLC. And one of the major uniqueness is I mean, we are trying to go as close to the limb as possible, because we know that the accelerations of the CMEs happens below the 2 solar radii. So covering with high cadence below 2 solar radii is one of the major science objectives of this VELC. So the current design is going up to 1.08 solar radii without vignetting. In principle, we can go up to 1.05 onwards. High spatial and spectroscopic observations compared to previous coronagraph, and high cadence observations of active region loops. Given the signal to noise ratios, we will be able to cover the higher cadence observations. And as I said already, coronal magnetic field measurements, especially for active regions, above the active regions. And in many cases, we can cover the magnetic field topology using the linear polarization signatures. And we are also going to have a first time put a CME detection logic on board so that we don't miss any of the CMEs which is happening. So keeping the data volume under control, this logic will help us to increase the cadence of the order of 1 minute without compromising on the data quality. So this would be the first time we will be doing a detection logic on board for it. And this is also a kind of an observatory class where you have a flexibility in operations. You can configure your field of view, you can configure your cadence, and you can also configure the spectroscopy for scanning. You can have a continuous raster scan, or you can even step depending on your science goals of the proposal. And it also carries a multi-operation door mechanisms for onboard calibrations, so that we do get instrument performance regularly checked and then corrected any of the data processing systems on ground. This gives you a view of the complicated optical configurations of VELC. I'll not go into the details of it, but just want to point out that we have a continuum channel which will image from 1.05 to 3 solar radii at around 5,000 angstrom. It's in the continuum. And this channel will mostly do the CME science. So we have a spectroscopic channel which has 3 simultaneous spectroscopic option, which is through a slit and field lens going through a grating system, And we have this 5303, 7892, and 10747 angstrom lines simultaneously carried out. And again, the image on the slit is moved through the combination of these field mirrors, which by moving these mirrors, we do scan the image on the slit. And we have a spectropolarimetric channel for the 10747 angstrom line, which is slightly, it's an advanced design of the spectropolarimetry, where we do the two-beam spectropolarimetry, which is a requirement in order to minimize the crosstalk introduced by satellite jitter and the drift. And that is achieved by using a polarizing beam displacer, and which displaces the beam in the wavelength direction, not in the spatial direction, so that you cover the full field of view without compromising on the performance of the polarimetry. This gives you a feel for what is the kind of spatial scales which it can cover, and the kind of cadence which the instrument is configured to carry out. So you can see that the imaging channel has a pixel size of 2.5 arcsecond square. So in principle, we get a 5 arcsecond square imaging in the system. And these are the spectroscopic channel where you have the spectral dispersion value, and also the spatial resolutions what it in principle can provide. But many of them we may have to do binning in order to gain on the signal to noise ratios. And cadence, you can see the seconds to hours cadence in the imaging channel, and especially during CMEs, we do get 1 minute cadence. And the spectroscopic channel, in principle, we can go up to 100 millisecond, but I think it would be mostly operated at in the seconds, in the second cadence level. Spectropolarimetry is operated at every 10 seconds you get one spectropolarimetric imaging, that is the Stokes imaging, every 10 seconds. And you can either sit and stare for that particular region for whatever time you want, or you can even raster scan it if you want to cover a certain field of view. And this is this will be operated in 2 different modes. One is the synoptic mode, which is a default mode of operation. During this synoptic mode of observations, which would be the most of the cases, it will be the case of operation. There will be a continuum image per hour if there is no CME, but if there is a CME, it will happen at 1 minute cadence. And spectra, we will have a raster scan once an hour if no CME. And if CME, then we plan to put it in sit and stare mode, so that as the CME propagates, you capture the spectral informations. Polarimetry, it's typically 3 raster scans per day with IR channel. So this is a synoptic mode. Of course, in the proposal mode configurations, we can always change whatever science objective demands for us to configure for. And all the cameras can be configured for its cadence and bending, except for the polarimetry. Polarimetry is limited because it is working on the principle of a rotating type modulator. So our rotation rate is fixed. So we can't change the exposure time of it, but we can change the cadence of it by bending more number of rotations. And since there is an onboard CME detection algorithm, if we need to go to the proposal mode, we need to disable the CME if you want to keep the CME mode operations continuing. Then coming to suit, so again, we have 4 major science goals. And I think my next talk will be covering most of the science aspects of it. So I'll not go into the much detail of it, but you can see that it does the dynamics of the both chromospheric and corona, and it also gives you a good context image for the VELC, where while VELC blocks the disk, suit will provide us the disk informations of it. So it has a large enough field of view to provide the context images. I mean, it has a field of view such a way that it covers our spectroscopic field of view up to 1.5 solar radii. So it can provide full disk UV images at high cadence, and it has specifically magnesium filters for solar flare studies and activities. And I believe in principle, since it has continuum band, broadband filters, it should also be able to detect some of the CMEs, if not the faint ones, but definitely bright ones. And again, gives us a contrast image with VELC. And Suit also has an onboard flare detection logic, so that whenever the flare is detected, it configures itself into a flare observation mode, where you get a pretty high cadence images for flare studies. Again, it is configured with a lot of flexibility in operations, and it also can track active regions. So if I fix on an active regions, I can continue to observe it for many days without any interruptions. And again, Suit also will operate both in synoptic mode as well as the observational mode, I mean proposal-based driven mode. This gives you a configuration of this Suit payload. You have an entrance apertures, and you have a off-axis parabola, which throws the light into the secondary mirrors, and it goes into the filter wheel combinations. So it has 11 filters to choose from, with the two filter combinations, and then it goes to the CCD camera. So this gives you a view of what are the filters which is used. You can see it consists of 8 narrowband filters, with the narrowest one is in the calcium band, and you also have this magnesium bands to cover the magnesium line dynamics, H and K lines. And it also has 3 continuum bands for the sun climate studies, and I think this channel can be utilized for CME studies also from the Suit. Okay, coming to the X-ray instruments. X-ray instruments is configured into 2 instruments. One is in solar low energy, as well as another is in the high energy part. Low energy covers from 1 to 30 keV, and the high energy covers from 10 to 150 keV. So that reasonably covers a reasonably very large energy range, and also has an overlap between the 2 instruments, so that it's easy to configure them and get a single spectra from both instruments. Some of the science goals listed here, and this can also do combined science goal with VELC and Suit instruments. For example, the flare CME association can be done, and flare prominence eruption studies can be done simultaneously. And as of I know, this would be the first time an X-ray flare instrument at L1, so that gives us a 24 hours capability of looking at flares. So it doesn't, you see the sun all 24 hours in a day. And it's also carrying along with the coronagraphic instruments, so flare CME studies can be done uniquely from this satellite. Where do we score much? I mean, if you look at the previous missions, and if I plot in energy versus resolution time scales, you can see that many of the previous missions fall either with a low resolution, large energy coverage, or a high resolution and a small energy coverage range. And we do fall in exactly in between the 2. Of course, there are other missions like SACS, XSM on Chandrayaan-1 and MinXS instrument, which is operated in this energy band and in this resolution. And we also have an XSM on Chandrayaan-2 currently operating and providing us very good data in this band. What is the advantage of that? I mean, here here I'm trying to show you some of the spectra obtained from the qual instruments of this payload to provide us a resolution which is of the order of 160, 170 EV, while RESI's resolution is of the order of 1 keV at these energy ranges. So we do have score a bit on the spectral resolution, and which allows us to study about the coronal abundances as well as the FIP effect. And here is an example of what has been done with Chandrayaan-1 and Chandrayaan-1 XSM instrument. What you see here is the abundances versus the first ionization potential. So what you see is any elements whose first ionization potential is below 10 eV is always enhanced compared to the elements above the first ionization potential. We do see it in the Chandrayaan-1 XSM instrument, but we also see that this enhancement do evolve with the flare phases. So what you see here is the flare light curve, and along with the FIP bias of an element called sulfur. Sulfur is an important element in the sense they fall exactly somewhere in the region of 10 eV. So that is neither in the low FIP nor in the high FIP region. So this, so we also have this HighEnergy X-ray spectrometer, and HighEnergy basically gives you the information about the particle accelerations during a flare. So this instrument captures the non-thermal Bremsstrahlung part of the X-ray spectra, while SOLEX covers the thermal part of it. So together, one can talk about the energetics involved in any of the flares. So this also has very high timing accuracies of the order of tens of seconds to study the quasi-periodic pulsations, what many of us see it in the high-energy flares. Okay, I'll skip this. So putting all these four instruments together, this gives you a synergetic science one can do with multiple payloads. One can start talking about global energetics by combining payload from, for example, VELC and X-ray instruments. And one can talk about the CME flare relations by combining all four instruments together. And coming to the in situ particle measurements, as I said, the aspects is configured as two packages, not two packages, two different instruments, covering all the way from 100 EV to about 20 MeV per nucleon. It also has multiple field of view, in the ecliptic plane as well as across the ecliptic plane, so that you sample the particle which is coming from the sun at all 360-degree in the ecliptic plane and 180-degree in the perpendicular directions. And it also has an CME arrival indication flag by looking at the ratio of the helium to the hydrogen abundances. And that flag is given in the telemetry data. So if you want to use it for any of the space weather signatures, we can look at this particular flag. This gives you a configuration of in the sun directions how the field of views are put in, and these two are in the south and north ecliptic pole, and there is also one instrument which is pointed towards the Earth if there is anything coming from the Earth side of the orbit. Then PAPA, while aspects does most of the particle as well as the composition analysis, PAPA does most of the electron spectrum. So in combination with aspects, it covers electrons, protons of the solar wind as well as the suprathermal particles, which can be studied along with the solar wind composition. So this is the science goals of these two instruments. And this is also configured with two packages, SWICAR and SWEEP sensors, basically using these guiding plates to collect the electrons and put them in the detector plane. Okay, these are the details of the energy ranges and the mass resolutions which it carries. And the magnetometer on board looks for the local magnetic field measurements. It's three BX, BY, BZ, all three components is measured. And it is configured as two instruments, one at 3 meter and another at 6 meter on a boom. So any of the satellite magnetic field generated can be compensated by looking at these two measurements. Okay, so I'll finally end up with this slide saying that though I think Aditya by themselves can provide much more information on the solar energetics as well as the space weather aspects of it, we also plan to use other observatories' support to enhance the science objective. I've listed few of them. I mean, there is a lot more other observatories are being discussed with. So we would like to utilize the MAST telescope, which you'll hear about it today afternoon, to complement what Aditya is going to do. And we're also looking for opportunities to use DKIS instrument for the coronal magnetic field measurements along with Aditya L1. And Helios and STIX onboard solar orbiter, it's already been talked about it to study the directionality of the particle accelerations by having them at two different vantage points. So basically solar orbiter and solar Parker probe is looking at keeping them at the multi-vantage point and then trying to study what are the enhanced science one can do compared to and having an individual satellite. So I'll stop there. Thank you.
That you mentioned in one of those slides, those are all fixed, or you can kind of tune to some other wavelengths in the spectroscopic
for VLC.
Yeah.
Yeah, it's all fixed wavelength. So these are the emission lines which are happening at those wavelength. So they are all fixed wavelengths. Okay, so it's a point to note. Though the instrument has capability of doing terabits of data, the data download per day is of the order of about 260 gigabits per day. So many of the onboard logics are built in such a way that most of our observational proposals as well as the observational modes are configured within this data volume. In case on a particular day, if you exceed the data volume, the next day's observations will be curtailed to a manner so that the data stored in the previous day can be downloaded. So on board, we have a data storage for about 3 full day of operations.
One last question.
Okay, so that is still in discussion with the payload team. What is a kind of data policy? Typically, going by our previous experiences, usually there will be a lock-in period for the performance verification phase for the payload, and we also have this guaranteed time for the instrument team. So, I mean, roughly, I would say it's of the order of a year before which the data may become public. And we are trying our best to make it public as much as possible so that the whole community can make use of this particular data. But there are few space weather related data which we are trying to see whether this can be made it open for the community so that the other observatories can also make use of this these signals.
Okay, let's. Sorry, we'll have to move on. So let's thank Shankar for his comprehensive coverage, and quickly call Srijit to give his talk on the Solar Ultraviolet Imaging Telescope. Trijit, can you finish your talk in 25 minutes? Is it possible?
Right.
So then I will give you at 20 minutes,
Sure.
5 minute.
Yeah.
Thank you very much.
Yeah, sure. Yeah, so I'll be speaking about one of the payload, which Shankar just talked about, the whole satellite, which has 7 payloads. In that, one of the payload is an imaging telescope. This is being built in this institute, or primarily being the PI institute is IUCAA, where you are currently sitting. And this is made in collaboration with multiple institutes. You can see the logos here, primarily with ISRO, which is our India Space Agency, and along with Indian Institute of Astrophysics, ISAR, and you can see different collaborations. Our principal investigator is Durgesh, and Professor N. Ramprakash is our instrument PI, and we have a quite large team working on the same thing. So I'm presenting this on behalf of the whole team here. Here is more information about the instrument collaboration, which is the institutes which are contributing to development of the instrument, and few names. So primarily Indian Institute, IUCAA, which is this institute, is our PI institute, and Indian Institute of Astrophysics, and ISAR Kolkata, which is also having SESI, and also URAU Satellite Center, which is, these colors are all part of the space agency. So different centers of the space agency are also contributing or providing technical support and developing some parts of the instrument for the suit, Solar Ultraviolet Imaging Telescope. So this is the whole image of the satellite. You see this small one here on the side. This is the one which is Solar Ultraviolet Imaging Telescope. And this will be the final view after with the radiator and with the cover panels, etc. What I'll do is I'll quickly go through the scientific objectives. Shankar has covered part of it. The why suit is important is because what is SUIT is it's a imaging telescope, as the name suggests, in ultraviolet range, and we use narrowband as well as broadband filters to cover the range of 200 to 400. And we are targeting at very high contrast and lows, almost like 100 SNR. That's our target. We also give so as you know this range, all the people working in solar physics immediately will understand that 200 to 400 range, or UV, covers almost photosphere to chromosphere, upper chromosphere. So we are covering the range in solar on the sun from photospheric level to upper chromospheric level, just below transition region. And we give almost near simultaneous coverage of that. And it's very important for the purpose of studying the coupling, because these days we know with things happening on the photosphere gets coupled, or the magnetic field gets coupled all the way to corona. So this covers a quite large height on the solar atmosphere. This also gives a unique opportunity to study the Sun-Earth climate studies, Sun-Earth connection, space weather, especially because ultraviolet is the one which is absorbed by solar Earth atmosphere. So obviously any variation in the ultraviolet coming from the sun has an influence on Earth's atmosphere. And if you see most of the earlier irradiance studies, most of them are sun as a star studies, continuous monitoring as sun as a star. Whereas here, we are having continuous monitoring of the sun because we are going to L1, first of all, plus, so all the 24 hours we are observing the sun, plus we are imaging the sun in a very good resolution and quite good cadence. So we are also going to get, other than the total solar irradiance and solar spectral irradiance, we are also going to get a spatial information of that, like from which part of the sun particular energy or ultraviolet rays irradiance is coming from. Like, is it active region contributing, how much portion of that, quiet sun is contributing what portion of that, whether the plage is adding to that. We get all those information in addition to the sun as a star contribution. So this is going to be very unique in that way, that we are going to get spatial information also about which helps the community with studying the sun-earth connections and Earth's atmospheric, how the ultraviolet is affecting. So in that way, it becomes a very unique payload. So if you all know this is the Blackbody spectrum, the black one is what you see from space. The red one is what you see from Earth's surface. You can see many part of that is absorbed. And this is, if you see, a little lower. So we are covering basically the region which is here, which is, you can see up to 300, 315, you can see little bit on our Earth's observatories can cover that. But below 300, it is almost not possible to see from Earth. We are covering from 200 to 400, this range of the Blackbody spectrum or the emission from the sun. This is challenging as well because, as you see, this is a rising region where within a small range, you have a big dynamic range covering this region. Hence, it was quite challenging as well to cover this region of this thing. And this is also very important, as I told you. Some part of that of 315, UVA and UVB, it reaches the sun's, Earth's atmosphere, at least if you have most of the observatory which are little high altitude observatories, whereas the one which is UVC, which it doesn't reach here, it's all absorbed or blocked by ozone layer. This also makes it important, as I told already, that if this ultraviolet is being absorbed by ozone layer or atmosphere, it means that it is charging up our atmosphere, or energy is getting dumped into our atmosphere. Since it's important to study exactly how much this UV is coming from the sun and which part of the sun, etc. If you convert this into the solar study, this is a diagram. I'm sure all the solar physics people here have seen this. So the solar atmosphere has divided this. X-axis is the height on the solar surface, and y-axis is the approximate temperature range. The solid line is the temperature profile from the model, and this is the density. The dotted dashed line is the density. So this is the region up to the photosphere and chromosphere, and after chromosphere you have the transition region. So this solar ultraviolet imaging telescope will be covering. We already know that this region from chromosphere to photosphere is mostly covered in visible and EUV. The most of the radiation coming from that is from this range, and above that it is mostly coming from the extreme UV and X-rays. So this will be the region covered by this instrument. We'll be observing all the way from photosphere up to upper chromosphere, just below the transition region. This is an imaging telescope with filters. It's not a continuous observation, but part of this, which I'll show in a moment. So this is a diagram. It shows basically the sun from all the way to visible or to X-rays with temperature increasing, and there's a magnetic field here. It's very obvious, and everybody knows that anything happening on the photosphere it's get coupled all the way to corona. You can see there's a magnetic field, it gets coupled to the corona. And this coupling is something which is of interest to the whole community these days, or from beginning, that how this magnetic field coupling happens and what are the physics in between that. And if you see this region is quite well studied these days because of thanks to SOHO, SUMER, and SDO these days, and Hinode. Whereas the region which is very little covered from space, of course, H-alpha, there are a lot of long-time observations from ground, but from space, the region which is very little covered is in full disk continuum, I would say. Of course, there are missions which has observed it in less cadence and in part of the sun. For example, orbiter has some observation, solar orbiter is having some observation this range, but not as a full disk and with high cadence. But this region is very limited observation. So we are going to cover this region, which is the near UV region in high cadence and full disk. Also, if you see this, this is a plot taken from that review by Benz on different, during solar flare, how the light curves looks like in different things. If you immediately, you will see that the region which is really missing is NUV here. The EUV is well studied, but NUV is not studied. And NUV doesn't behave like H alpha. There's a poster by Manoj here. You can see that we have been looking at some of these NUV light curves. Interestingly, NUV is not like H alpha. It is more of like, it behaves more like hard X-rays. It peaks at that similar time scales. So one region which is really missing here is this NUV, and the Solar Ultraviolet Imaging Telescope is going to fill that region. We are going to see many flares in this region, and we may have a better idea how the flare develops with time in near ultraviolet region. So just combining, collating all this, what I talked about, the major science goals, which just now Shankar told, one of them is coupling and dynamics of solar atmosphere all the way from photosphere to upper chromosphere, and in collaboration with other observatories like SDO and Solar Orbiter, we'll be able to also connect all the way to Corona. Also solar flare studies, as I just told, and we also can study some prominences. Our field of view is little above. I'll just come to that about our field of view. We will be able to see some of the prominences and very bright CMEs, as Shankar just told, because some of these prominences erupt, and we'll be able to observe that at that location of eruption. Also for sun climate studies, which I covered already. And it's very important, and there is a lot of interest to understand that how relevant is this variability in UV irradiance, because though the total irradiance, the TIS, variation is very small over solar cycle, it is understood these days that whatever fluctuation is there in the total irradiance, the major contribution comes from the UV side. Almost 60 to 62% comes from the UV side, the variation. So hence this variation in UV irradiance is of something very interesting to study. This image is taken from IRIS. Of course, IRIS doesn't see the full disk, it only scans a small region. So it's a stitched image of the whole sun. IRIS has this, they do once in a while scan the different regions and they stitch together to full disk. The reason I took IRIS is one of the only payload data which are available to us, which is in between 200 to 400 or in the middle of that magnesium, which is of a lot of interest to us as well. So you see these bright regions, the active regions look very bright in magnesium. Our FOV will be this large region, which is almost like 1.6 R0. So from the disk, we have quite a lot of distance where we are seeing. So if there are things happening in this region, like for example, bright CMEs, which is taking off, or prominences, we will be able to catch them in some of our filters. This reason to choose this also is because, I'm sorry for this. The reason to choose 1.R0 is also because there is another payload on the same Aditya, which is a Coronagraph. We wanted to have a common region. So the yellow one is the field of view of the ultraviolet imaging telescope. And what you see here, this is the image and this is the scanning region of the VELC. The red lines are the slits of the scanning things, which Shankar just showed earlier. So we have a region which is overlapping with SUIT and VELC, and VELC is scanning here. So this will give so whatever you see on this coronagraph, we will have a good understanding where it comes from and what happens below that region. So this will be as a combination, this is going to cover the whole from the disk all the way up to 3R0, solar radius. This already Shankar showed you. These are our 11 filters. This forms the heart of our payload selection in things. This 4 at 214 there is a filter with 5 nanometer FWHM. Then this 4 forms this magnesium line. So magnesium index is something of a lot of interest to the community because it's a proxy for Lyman alpha, and we know Lyman alpha varies a lot during flares, for example. And we can create magnesium index. Not just we can create magnesium index, we can also get a spatial info. We can get a magnesium index image of the sun. So we know exactly which region of the sun this variation is happening, and in quite good cadence. And also there is a 300 and 388 line basically to study the photosphere, and there's a calcium line with very good 1 angstrom FWHM. And we have three broadband filters covering the range from 200 to 400. So this is just an image to show the region or the response curve of our filters. So you can see these broad ones are the broadbands, three broadbands, and we have 8 narrow bands here. I'll quickly show this curves in a little more better way. So these 3 are the broadband ones, and these 8 are the narrowband filters. And just for imaging, this is our filters are very similar to the SOFI, which was a balloon experiment from Max Planck. You see that this is a SOFI image, and if we put our resolution, their SOFI resolution was 0.02, whereas ours is 0.7 arcsecond per pixel. It will be a little bad than that, but we will be able to see quite good in high resolution. I'll quickly take you through this payload. So this is an off-axis telescope, as just now you heard in the previous talk. What we have is an entrance aperture here. We have a primary, the light goes to the secondary. This is off-axis hyperbola mirrors. And it goes to a shutter mechanism here, which controls the exposure time basically. And then we have 2 filter wheels. The light always passes through 2 filters. One of them is a science filter, another is a ND filter to cut down or to adjust for the dynamic range we are facing. As you all know, 200 will be very not so bright, whereas 400 is going to be very bright on the sun because blackbody is rising. So we need some ND filters or bandpass filters to cut down the light after it passes through the science filter, or one of them. So it passes through 2 filters always to adjust for the dynamic range, plus choose the spectral range for science. And then we have a lens here which can be moved for adjusting the focus in case if there is any defocusing happened due to the launch or anything. With time, we have a focusing mechanism here and to adjust to get a very good improviser image. And we have a 4K CCD here with all the cooling mechanism. That's what the payload is. And these baffles are for controlling the stray light, etc. This is another image, another view of this payload. So just to give a CV of the payload, it's 200 to 400 with 11 science filters. The field of view is almost 0.8 degrees, which is 1.6 solar radius. And the resolution is 0.7 arcsecond per pixel. And we are targeting very good contrast and image quality with 80% of encircled energy to be fall in 1 pixel. And the size is, the primary mirror size is almost 140 mm and effective focal length. And we have a of 3.5 meters. And we have a detector which is a 4K CCD. We have 2 types of imaging. One is a full frame image. As I showed you already, this image is taken from iris stitched image in MG2H. This is a full disk will be a 4K 496 pixel, which covers almost like 48 arc minute to 48 arc minute. And the frame time to read the full frame, what frame time I define is the time it required to record the full time is around 16 seconds. That's the best cadence possible if you want to observe in full disk. And the size is 32 MB of this image. It's quite big. And we also have an on-chip binning option, especially for space weather applications when we want to take more images, where it can be made into a 2K image on CCD itself. The advantage being the size comes to 8 MB, and the readout time also reduces from 16 seconds to 13 seconds. We also have an option to choose a smaller region of the sun. We can define a smaller region of interest on the sun. And decide to read only this region and just remove all other parts. What happens is advantage of being that, for example, the region is choosable, we can adjust it, but by default we are planning to use it around 8 arc minute by 8 arc minute. It's cover almost 700 pixel by 700 pixels. Advantage being you can see the frame time comes down to 4 seconds to read this, so the cadence can be improved a lot, and the size comes to almost 1 MB. So you can do a better high cadence observation. If somebody is interested to say, I'm not interested in the full sun, but only an active region or a prominence or some part of the sun, like pole or whatever. And we have something called observation modes. So basically a mode is combination of these 11 filters, which one, pick and choose which one you want and what sequence you want to arrange them, one after the other. And you choose, I want a smaller region of interest or a full frame. And also how much duration you want, how many times you want to cycle through your sequence, etc. That's what we define as a mode. So it's basically we have these 11 filters, and this is a combination of this. We have a default mode, which we call the normal mode. If there is no proposal from the community to observe a particular sequence, we have a particular defined mode. So default mode is to go through all the filters, 11 filters. So we go through the smaller region of interest. We will decide a smaller region of interest every day, which day to observe or during a time. And we will go through the 8 NB filters in that, the narrowband filters. Whenever it comes to magnesium 2H, we take a full disk image in 2K, so that every minute we have a full disk image. It is useful to give a context to the VELC, the coronagraph, also to the space weather applications. So this keep going around as a cycle for almost 30 minutes, 26 minutes. So one frame time is 4 seconds here, as I told you. But there are 8 filters here, and one of them takes more time because it's a full disk image. So the cadence by default will be, by cadence what I mean is to come back to the same spectral image again after one cycle will be around 40 seconds in the default mode, since we are using all the filters, one after the other. The full frame sequence, after 26 minutes, we take the full disk image in all the 11 filters again. So this cadence will be every 30 minutes because of 26 minutes we are observing only smaller region. So every 30 minutes we have the full disk image of the sun in all the 11 science filters in the default mode. But as you know, in sun there are issues like a flare can happen at some time. It is unpredictable. So we have an onboard algorithm which looks for the flare. What we do is we have 2 X-ray payloads on the same satellite, as you just heard, which is basically covering 1 to 30 keV and 10 to 40 keV, this Helios and Solex. We have a hard wire line coming from that to our payload, which gives an information that what is the X-ray count happening on the sun. If the X-ray is increasing on the sun, immediately they give a trigger to us saying that, see, the X-ray is going above the noise level with certain threshold, which can be programmable again. Once it goes to that, we have an internal algorithm. It moves to that and start to localize where this is coming from on the sun. Once we find which region on the sun it is coming from, it automatically moves to a ROI mode. Even if it was in a full flare, if it was in the normal mode, it just moves to, it just picks up that region which is bright, and it cancels all the existing proposed mode if a flare is happening, and automatically it goes to a flare mode where it starts observing in this smaller region, or the region where the flare is happening in with a mode which we call it a flare mode. So as a part of the normal baseline mode, this is the one which I explained. We also have a flare mode. First part of the flare mode is to localize where this is happening. We are using the magnesium filters to do that, and then it goes to very similar thing here as of now. But again, all these are programmable, and proposal can be made to change these sequences, make it faster, etc. If it is within our data bandwidth and doable in terms of throughput, etc., we will be able to do that. There are also science case-driven modes. These are proposed by community at different times of this development. People want to observe, not observe all the filters, want to observe only 4 of them. In case of prominence, for example, we know that 300 may not make much of a sense to look at the photospheric line in prominence. So advantage of choosing less filters is being the cadence will be faster. And there are also different, I'm not going to the details of that, but these are the few science case driven modes which we are already programming into that, but we have an option also to add more science case driven even after launch. This is just to summarize or just give a view of that. This is a satellite, and this is the small one sitting here on the corner, is ultraviolet imager. After closing down everything, it looked like that. We have a radiator to control the temperature, and we have, this is our entrance aperture door. Okay, I'll stop with this, with few images of our development happening. Yeah, that's all. Thank you.
Thank you, Srijit. Any questions?
So, can you use this narrow band filter, for example, 0.1, 0.4, that is 1 angstrom, 4 angstrom. Do you have a thermal control for that?
Thermal control?
Yeah, for the narrow interference filters.
Yeah, so we have a control on the ambient temperature, which is 20 plus or minus 3. It's very stringent demand, and Space Agency, which is taking care of that, they have assured it will be like that. Not only for the filter purpose, even our focusing, it's important that the temperature is maintained and it's not varied. So we are very hopeful, we are very sure that the temperature, the ambient temperature will not be varying much from 20 degrees. Plus, you should remember that there is a thermal filter in the very beginning. If you see the starting part, and almost all the light from 99% of the light from the sun is thrown out, only a small percentage of the sun, that also coming in the UV range, is taken in to the primary. So we are not expecting a lot of heating happening because of the sun.
Yeah, I'm not telling about the sun. Okay, did you calculate what kind of a shift in the wavelength if the temperature goes, for example, plus or minus 1 degree?
So when we, from the vendor, which is the earlier Bar Associates, which is now Materion, we had given a very specific spec on that how much the temperature can vary. So with 1 degree, it is some picometer change. And we are sure that 3 degrees the maximum it can happen. So even if shift happens, it is going to be in the range of picometers.
And what about the, one more question, I guess. What about the wavelength shift because of the field of, means because of the incidence angle? Do you, because these are narrow band filters, 1 angstrom is very narrow. So you will get a field, so the wavelength shift from the center to the, when you go to the limb.
So we have calculated that, how much is going to be the FOV effect, especially if there is a tilt to avoid ghosts, it's going to be more critical. So for example, calcium, which is 1 angstrom, we are not tilting it at all. We are trying to, so that this effect will be minimal. And ghost, we have calculated the effect of that on the ghost, for example. But within the FOV, it is coming within our FWHM, at least the solar disk. Of course, as you go to the prominences, it may shift a little bit out, but within the disk, it is coming within that range.
One comment is that you have nowhere put a dimension scale. So at least put a scale to show.
Oh, okay.
What is the dimension?
Oh, okay. Okay, I'm sorry. Yeah, I should have put. So I can just tell quickly. This size is around 1 meter in length and almost half a meter in width. So the bench size is almost 1 meter by half meter. Yeah.
You have said that you will focus whenever there is a defocusing or something.
Yeah.
But you will come to know about it only after quite some time.
Yes.
Right?
Yes.
By that time, the event might have over.
Yeah. So it can.
About that.
Yeah. So there is no chance of getting a defocusing as such. So if you see here, here is a mechanism. We are not expecting any reason to defocus every day. The only thing is by launch time, because of vibration and all, something can happen. Or with time, long time, something can happen in case of, because of thing. So even if few images, when we see the images only, we'll know that there is a problem. But through commands, we can move this lens forward and backward a few steps using a stepper motor on this. So we can adjust it so that the new images will be better. Of course, we'll see it when we see the images.
You mentioned about the flare mode.
Yeah.
So what timescales you'll be looking at once the flare you identified from hard X-rays? How long will it take the point?
Yeah. So it's a good question because that's, for every flare it is different. In fact, the time from when we look at the light curves, you see that the hard X-ray to the flare peaking in soft X-ray or in UV, that's not a constant thing. It varies from case to case. But the time we require as of now is 1 minute around. After getting the pulse, because we need 4 images of 16 seconds each, around 1 minute time, we will be able to localize. So in 1.5 minutes time, we will be able to start observing in that region. That's what, as of now, our capability will be. If the signals from the X-ray payloads comes. If there's a flare where the X-ray payloads are not able to detect, we have an internal mechanism of self-trigger. It looks at, it keeps monitoring our own image to see there is an increase in flux in some region in UV. Suppose there is a flare which is in UV but not seen in X-ray, suppose. Still we may be able to catch it, but in that case it will be around 4 minutes time.
Okay, so we'll move on. We will thank Srijit.
Thank you.
And then invite Shimizu-san.
Can keep it here or here?
Put it here.
So there is no display.
It's undetected.
Detected.
While waiting for Shimizu-san, I just wanted to remind all of you of the enormous contributions made for the Aditya project by the late Professor Yuva Rao. He was a great driver, and he sat there and almost literally pushed the spacecraft to L1. So this is just to remind his contribution.
Thank you.
Shimizu-san, I will interrupt you at 20 minutes
Okay.
and give you a 5-minute sign.
Okay.
for that.
Okay, good morning. I'm Toshimizu from ISAS of JAXA Japan. I'd like to talk about the Solar Sea UVST. That's our new mission. And in addition, at the end of my talk, I also like to briefly discuss future strategy for space observations in Japan beyond the Solar Sea UVST. Why do we study why do we study the sun? Scientists has a variety of different answers, but there is two major answers. One is we like to understand physical processes governed in plasma universe by observing solar plasmas, which is located closest to us. Another answer is the sun gives a variety of influence to the heliosphere, the Earth, and planet. There are three key objectives in solar physics that should be tackled in this decade. How hot and dynamic outer atmosphere is created, what causes flares and plasma eruptions, how the solar magnetic field is created and maintained. The new observations are most powerful tool for better understanding of the sun in terms of these science objectives. In Japan, IUCAA provided soft and hard X-ray imaging observations in 1990s, revealing some pieces of evidence for magnetic reconnection in flares. After that, we realized Hinode as a high spatial resolution on-orbit observatory to understand the magnetic origin of the activities in the upper atmosphere, in the corona. High-resolution observation with Hinode has revealed the solar atmosphere is full of MHD processes, including waves, magnetic reconnection, magnetic convection, and MHD instabilities. Which is the button? This one, okay. One of the unexpected discovery with Hinode is chromosphere is more dynamic than ever thought. Triggered by such observations, IRIS was planned and realized quickly by NASA in 2019. IRIS provides us a spectroscopic measurement to quantify dynamic chromosphere. This observation, this line of observation is directed to higher spatial resolution, but the field of view is quite limited. Our Solar Sea EUVST is in this line. On the other hand, observing the full solar disk is very, very important for various purposes, such as probing convection zone with helioseismology, for monitoring space weather phenomena, and so on. Following the successful SOHO SDO, India and China will be launching their own solar physics satellite in a couple of years, adding new observational capabilities. It's a very, very nice and useful for us. Our solar CUVST mission is a new mission that the solar physics community in Japan is promoting as the next solar physics mission with participants from United States and the European countries. The EUVST, that's the abbreviation of the EUV High Throughput Spectroscopy Telescope. This mission concept was down-selected as a candidate for JAXA competitive M-class missions 1.5 years ago. This is the science objectives of the mission. Observing the solar atmosphere is very, very important for understanding how the plasma universe is created and evolved. Also important for understanding how the sun influences the Earth and other planets in our solar systems. We know the interplay of magnetic field and plasma create a variety of behaviors in solar atmospheres. There are not only quasi-steady ones, such as the heating of corona and solar wind, but also the transient ones, such as flares and CMEs at the large end. A key observation for understanding such behaviors is to understand how the energy and mass transfer and energy dissipation happened in the complicated solar atmosphere. Two science objectives are defined for this mission. One is to understand the fundamental processes lead to the formation of the solar atmosphere and solar wind. The low beta corona with a temperature above 1 million Kelvin is magnetically coupled to the high beta photosphere. The Hinode solar optical telescope observation have clearly revealed the dynamic nature of the elemental magnetic structures in chromosphere. The elemental magnetic structure in chromosphere is rooted into the magnetic patches distributed on the high beta photosphere. When we look at the corona by another coronal instrument, the resolution is because with two different spatial resolution, it's impossible to trace the energy and mass transport from these fine dynamical structures into the corona, also inside the corona. That's the reason why we need to go to the higher spatial resolution spectroscopy to diagnose, to evaluate the energy and mass transfer happening there. Oh, sorry. Second science major objective is to understand how the solar atmosphere becomes unstable, releasing the energy that drive solar flares and eruptions. In the flare scenario, magnetic reconnection has been considered as a central energy converters. Magnetic reconnection is developed closely associated with MHD instabilities of more larger magnetic structures. The trigger mechanisms are most unknown area why such a reconnection and MHD instability is developed in the short time scale. That's the most one of the important area. So in the next missions, we should address why magnetic reconnection is so fast, how the large-scale structures is unstable, and also the what is the trigger to accelerate such processes. To achieve these science objectives, EUVST is designed to make 3 significant advances. One is to seamlessly observe all temperature regime of the atmosphere from the chromosphere to the corona simultaneously at the same spatial resolution. Such spatial resolution should be achieved to resolve elemental structures of solar atmosphere. The instrument should track their changes with sufficient cadence. The instrument obtains spectroscopic information such as velocity, density, temperature, and so on dynamics of elementary processes taking place in the solar atmosphere. This is a summary of science and instrument design requirement. The driving requirement on the investigations are defined from science objectives and their goals, such as temperature coverage, target spatial scale, temporal resolution, target size, and velocity resolutions. The driving requirement provides the design requirement for mission instrument, such as wavelength band should be observed, spatial resolution required, effective area required, field of view, and spectral resolutions. The EUVST consists of the minimum number of optical elements for a spectrograph to achieve the high throughput performance. That means we have primary mirror, slit, gratings, and detectors. Off-axis primary mirror make an image on the slit. The slit selects a one-dimensional portion of the image, which is incident onto the 2 concave diffracted gratings, which disperse the incident photons in the spectral directions, which are imaged on 4 different detectors. In addition to the spectrograph, EUVST also has an imager for monitoring the dynamical natures around the slit is located. This telescope has a fairly long telescope, 3.8 meter, and this instrument will be developed with hardware contribution from United States and European agencies for achieving the rich spectrograph functions. The EUVST is mounted on the top panel of the bus module with the solar array panel deployed at the both sides. This spacecraft is well fit to the fairing envelope of the JAXA Epsilon vehicle. Spacecraft will be into the sun-synchronous polar orbit, which is the same as the Hinode. High pointing stability will be achieved based on the Hinode heritage and knowledge. Let me look at a few key performance. One is the spatial resolution required, which is 0.4 arcsecond is required. It's about 7 times higher than the Hinode ice. It's 7 times means the power to resolve about 50 times smaller feature in the area size. This is a picture of sunflowers showing the just overall structure of the sunflowers at the left figure. But having 7 times improvement in the spatial resolution, we can clearly distinguish each petal and seed. This is something like the sunspot, and the petal is something like the magnetic loop coming from these center portions. So the 7 times improvement would be clearly distinguish the magnetic loop routing from the magnetic element at the solar surface. Lower panel shows the comparison of the corner images taken with high C and the ice, 10 times difference. High C data clearly shows a very, very complicated fine structures existing in the magnetic structures, and the EUVST can provide the spectroscopic information for such a detailed, complicated structure existing in the magnetic structure in the corona. The high throughput is also another important performance EUVST will have. Left panel shows the effective area of the instrument as a function of wavelength. At a short wavelength channel, peak efficiency is a factor of 10 improvement compared with the ice. In the longer wavelength channel, it's 40 times over Soho-Suma. High throughput will provide us a high temporal resolution even with such a single slit spectrograph. At the right panel shows count rate of spectral lines to be observed with EUVST as a function of the plasma temperature. We have a variety of spectral lines providing a seamless access to plasma temperature from the 10,000 Kelvin through the 20 million kelvins without any gaps, temperature gaps. This is the latest mission status. The mission is now in the mission definition phase. It's a pre-phase A2 in JAXA term. At JAXA, ISAS of JAXA, currently review process is ongoing to make the final selection for competitive M-class mission number 4. Actually, this week there is question and answer process is ongoing now on internet, and I'm participating to that. And the next week we have a review, important review meeting is scheduled, and that's a important timing to make a final selection for competitive M-class mission number 4. Solar CUVST is the only candidate for currently candidate for this mission slot. Another good news is that NASA has chosen this mission proposal for a Phase A mission last September, and US colleagues are now in Phase A study. Also, the European colleagues are working hard to coordinate with each national agencies for providing some hardware component. 5 European national agencies with ESA will be moving forward to their participation once a mission is finally selected by JAXA soon. The Solar CUVST is an important instrument to diagnose the plasma existing in upper solar atmospheres in the later half of this decade. The NGSPM SOT report, that is the Next Generation Solar Physics Mission Science Objectives Team report, was published 2 years ago and submitted to the NASA, ESA, and JAXA. That report recommended the 3 minimum set of instruments with which the next mission can address the greatest number of science objectives and maximize science return of the missions. Considering the current agency situations, resources, ideal situation is to realize all of these instruments on single platform, but it's not possible considering the current agency's resources. So our approach is to realize these instruments by having a constellation of the mission and facilities. The most important instrument, high-resolution coronal transition region spectrograph, will be realized as Solar CUVST as a JAXA competitive M-class mission. I hope the high-resolution coronal imager will be realized by some way by NASA, such as NASA MIDEX mission. Also, high-resolution chromospheric, photospheric image magnetogram spectrograph that requires a meter-class telescope. Currently, it's difficult to fly such a large telescope on, to the orbit, but we have a 4-meter ground-based nice telescope, DKIST. I'm very, very impressed by the first light images and movies released last week. And the solar CUVST observation should be closely coordinated with DKIST. Already we are started our discussions with DKIST team. And also the coordination with ground observatories in Asia is also important. Also the coordination with new Indian, Chinese satellite is also useful. Also the EUVST will fill the important gap existing between the solar surface and the in situ measurement to be carried by the Parker Solar Probe Solar Orbiter and Bepi Colombo. And also the punch will be observing the outer atmosphere from 5 solar radius. EUVST spectroscopic measurement here will be physically link the data coming from these instruments with in situ measurement. This is a fact sheet of this new mission. We have 2 science objectives, and we have a high throughput spectroscopic telescope to quantify how mass and energy are transferred with first ever capabilities. That's spectroscopy with wide temperature coverage and high spatial and temporal resolutions. Finally, I'd like to briefly talk about the strategy, future strategy beyond the solar CUVST in Japan. This is a JAXA opportunities for space mission in 2020s. As you can see, most of the available launch slots are almost identified and chosen. Our EUVST will be selected as the 4th slot in these categories. That means we are now facing it's a time to also think about what is the future, our strategy beyond the 2030s. What kind of approaches should be made in 2030s, 2040s? Already such discussion has started in Japan. This is a general strategy beyond the solar CUVST. Hinode operation will be continue for a while, and our current prioritized mission is to fly solar CUVST in middle of this decade. It takes about 20 years from the launch of Hinode to the solar CUVST. It's a long time. And in order to promote new missions, we need to develop the new generations. New generation scientists need to have the skill to develop the space instrument, also have experiences. We use small missions such as the sounding rocket experiment and the balloon experiment to develop younger generation skills and experiences. We have 3 directions available beyond the solar CUVST. For example, some scientists, with help from other nearby community, are working to propose Phoenix mission for Epsilon competitive M-class mission. Based on the technology demonstrated during the FOXY third flight, the FOXY will focus on the particle acceleration in magnetic reconnection, which is important unveiled fundamental physical processes for astrophysics. Also, we have two different directions that both of them are big missions. One is a large space magnetogram. The other is a mission escaping from ecliptic plane for polar observations. Large space magnetogram mission is to diagnose magnetic field in low beta upper atmosphere, which requires a lightweighted meter class space telescope. We need to look into the result coming from the DKIST, whether we can propose such large space magnetogram. But one of the good things is diagnostic method have been investigated by using the various small missions such as the CLASP, Sunrise, DKIST. The mission escaping from ecliptic plane, that concept was studied in Japan in 2010 as a large strategic solar sea plan A mission. At that time, we didn't choose these options because technical readiness level of required technology is insufficient to proceed these directions. But now we are also thinking of these directions as well. Okay, this is a summary what I discussed in my talk. Solar CUVST mission is our new mission. Will have much advanced capabilities such as seamless temperature coverage, high spatial resolution, high throughput for two major science objectives. The current target launch date is January 2026, which is still at the end of next solar maximum. We have three options available beyond the solar CUVST. If we choose a large mission concept, we definitely require a large-scale international collaboration, and that's a very, very challenging one. That's all. Thank you very much.
Thank you so much. We'll have some questions.
This UV telescope, you will have only a spectrograph, right? You don't have the measurement of polarization measurement capability.
No polarization capability, just a spectrograph.
Yeah, so these spectral lines, the main ones are magnesium 1 and magnesium 2. Are there inversion techniques developed for these lines yet?
You are talking about what kind of spectral line available, right? Yeah, a huge amount of the spectral lines are available, and the wavelength channel is fairly wide in EUV. It's a short wavelength channel is short channel ice have been observed. Also, the 46 to Lyman alpha channel is also covered. So there's so variety of spectral line available in this channel.
Shankar. Yeah.
It's very nice to hear about this UV instrument, because some of the temperature range which is not available in Aditya is available here. So it will be a good complementary data which we will get from probably 2025.
Oh, yes.
I just have only one, this 0.4 arcsecond resolution. Is it at which wavelength, this resolution?
Sorry?
The spatial resolution of 0.4 arcsecond.
0.4 arcsecond is for spectrograph as well as slit jaw imager.
Okay.
Yeah.
At what wavelength it is? At what wavelength?
For slit jaw?
Yeah.
Slit jaw is actually slit jaw imager is focused on the chromospheric line located. How to say?
Or the wavelength.
Yes. Yes. Yeah. As I said, the 0.4 arcsecond is not only for spectrograph but also a slit jaw image. Yeah.
Okay. I think we should move on to T. Let's thank the speaker. And shall we try to get back at 11:30 so we can get back on time? Or? No, make it half an hour break. Yeah. 11:40. So let's assemble at 11:40.
Yeah. Thank you very much. Nice to see you.
Is there water? Is there water in that? Or is it? Yeah, there is.
हेलो 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 ये सर थोड़ा मुंह के पास हेलो 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 hello, hello, hello. Hello, hello. Hello, 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 check, hello. Hello, 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 check, hello. Hello, hello, hello. Hello, hello, hello. Hello, hello. Hello, hello.
Test, test. HighEnergy. Test, test. No. Yes, no. Put it up higher in my script. How about that? Test. Yeah, that's better. Okay, let me get this.
On.
Is it on? It's on now.
On. Mute. On.
So this is mute right now, right?
Yeah.
On.
Yeah.
And mute.
Do you want some more audience? Okay, we'll wait.
Yeah.
Pointer. Main pointer, forward, backward.
So.
This pointer. Forward and back.
Oh, forward and back.
Forward and backward.
Okay, thank you.
Okay, welcome back after the break. And since it's the first day of the meeting and people are meeting each other over a cup of tea, things got delayed. So I hope we can, how do we handle it? Same time, let it slip into lunch? Okay, so I have the organizers' permission to be very lenient about, lenient in the sense not restrict within the other time, within the allotted time. So now I invite Sarah to deliver her talk. And Sarah, I will warn you in 20 minutes so that I show a 5-minute sign, and then you have the option. So if you want more questions, you can stop at 25. Okay?
Okay,
thank you.
All right, thank you very much for inviting me. I'm very happy to be here to talk about the Punch telescopes. I am the project scientist on Punch. Craig DeForest is the PI. We have a great science team, including international collaborators, including Dipankar Banerjee, who I see, who is our liaison with Aditya. There we go. So one of the motivations behind Punch has to do with the fact that heliophysics, as we know it, really is to some extent a divided community, divided between solar physics and heliospheric physics. And part of that division originates from the fact that we actually really work in different observational regimes. With solar physics, our understanding of the sun is very much shaped by remote sensing observations. We have such wonderful observations of images in movies of the sun and the solar corona, and we can see coronal mass ejections, we can do spectral analyses, spectropolarimetry, all sorts of things. On the other hand, and in a very complementary sense, heliospheric physics largely studies the solar wind by making in situ measurements, which allows tremendous it allows you to actually quantitatively measure the solar wind that's flowing by and not interpret it from remote sensing. So it is incredibly powerful. But of course, you're measuring in a local region. So these are fundamentally different. Now, Parker Solar Probe represents an example of how the in situ measurements of solar wind heliospheric physics has now gone right to the source and is measuring right at the sun. And Punch represents similarly an attempt to look at remote sensing, but to take it beyond the sun, well beyond the sun, in terms of a large field of view of the whole sun and solar wind. Now, as you know, we have observations that take us beyond the sun into the solar wind. We have this nice movie that was made showing the sun stretched out so that the sphere of the sun, the circle disk of the sun, is looking like a rectangle, extending out to the solar corona, the inner heliosphere, and then to near Earth. And it allows you, for example, to look at this nice coronal mass ejection, which is going to go out and track it all the way through the heliosphere to the Earth. These were stereo observations taken at quadrature. But I want to call your attention, in particular, to the gaps in this image. And these gaps are actually very important in terms of letting us get at some fundamental questions in solar and heliospheric physics. For example, there seems to be a textural shift between these coronal observations and these observations in the inner heliosphere. Is this because there is a qualitative difference? Or is it because these instruments, these coronagraphs and heliospheric imagers, were not designed to really observe things in the same way? We see these CMEs in these very large-scale structures, and we can track them, but we really can't see how they are connected, especially the smaller scale structures. And we can't really see, for example, how coronal mass ejections evolve and move in 3 dimensions as they move from sun to Earth. And this is important because we put a lot of energy in trying to understand the source regions of CMEs. But if the CME that leaves the sun is very different than the CME that hits the Earth or other planet or other spacecraft, then it becomes very hard to interpret what we're looking at. So that is the motivation behind PUNCH, which is a NASA Small Explorer mission. We want to understand the young solar wind. We want to understand how the corona gives rise to the heliosphere and the solar wind. And our approach is direct, continuous 3D imaging of the entire outer corona and the inner heliosphere. The unique aspects of PUNCH I can really summarize in 3 things. First of all, the field of view, which I'm going to show you in a moment. Second of all, the sensitivity, which is 10 times better than anything that's gone before. And third, the fact that we get polarized brightness and brightness throughout our images from the corona and in the solar wind, which allows us to do 3D location of structures. Our structure of the mission is a constellation approach. We have 4 synchronous small satellites. We're in low Earth orbit, and we have a 2-year planned mission with a launch in early 2023. So we will be up at the same time as Aditya. Our status is that we have been selected for flight, so we are in phase B. Here's kind of an image of what's going on with these 4 satellites. So we have 3 wide field imagers. These are like the heliospheric imagers you're familiar with on stereo. And 1 near field imager, which is like the outer coronagraphs that you're familiar with, for example, on stereo or LASCO. And they're in this configuration in such a way that when they each take an observation with these field of views represented in these kind of rectangular, pseudo-rectangular shapes, they're mosaicing to fill the full field of view with a cadence that allows, for example, in the lower regions where we're measuring the flow that I'm going to show you, a cadence of 4 minutes. So this is the PUNCH field of view in terms of solar radius. This is done in elongation angle. 1 degree of elongation is basically 4 solar radius. So we have this field of view in terms of solar radius. But I want to call your attention to this field of view because it is that true circular field of view that we have. So we are filling the blind spots that are between the existing coronagraphs and heliospheric imagers. We are also filling the blind spots that are above the poles where we really have never observed the solar wind. So this is, for example, the coronagraph for existing coronagraphs and stereo, and these are the heliospheric imagers. But PUNCH is filling in this entire region. So our science goals, we have 2 basic overarching goals, objectives. One of them is the ambient solar wind, and one of them is the dynamic solar wind. So let me start with the ambient solar wind. And here, our sub-objectives are to look at the global evolving solar wind flow, to image the Alphane zone, which is the boundary of the inner boundary on the heliosphere, and to look at solar wind microstructure and turbulence. So let me start with that global solar wind flow. Now, what I'm showing here is was a very it was a campaign that was done with the stereo Core 2. It took place for 72 hours, and the cadence was sped up to 5 minutes as opposed to 20 minutes, which is the Synoptic Core 2 observations. And what's the word? It basically, I'm blanking on a word. Never mind. It was able to see things with much finer structure. So the outflow was visible everywhere because they're small moving features. And the outer corona is dominated by this sort of wood grain structure. Let's see if I could get that movie going again. There's a smooth background and a star is removed, and so what you're seeing is actually 3% of the imaged light. So this has been heavily processed. But then it was processed still further by doing a running image following with the moving frame of reference of the flow that was observed, and this movie was made. And so now you can see all these clumps of solar wind that are constantly moving out. Punch is going to use this kind of image processing analysis in order to map the flow of the young solar wind every 6 hours. It's going to make all these data available. It's going to come out with basically flow as a function of height further out than this field of view. And I want to compare this. The only thing we have that's at all like this, really, is the Ulysses measurements. And Ulysses really kind of gave us a remarkable view of the flow in the solar wind by observing in its orbit where it went in the space of about, I think this was about 6 months or a year, where it went from one pole to the other. It observed at 4 AU the solar wind flow and mapped out the flow structure at solar minimum and solar maximum. But this was done once every 6 years. Actually, this was at 1 AU where it was making the observations. Whereas Punch is going to be doing that every day, every 6 hours at multiple heights, close in and out into the young solar wind. The second science question has to do with turbulence. And here we have an interesting phenomenon, which I mentioned very briefly earlier, which is that there seems to be a qualitative difference between what we're seeing in the Coronagraph, where we see these sort of radial features flowing out, and what we see in the heliospheric imager, where we see clumpy or fluffy type structures. And the question is, are we seeing the onset of turbulence? Or again, are we seeing something that is instrumental? The beta equals 1 surface. The surface where the sun's magnetic field becomes too weak to stabilize the flow is going to happen somewhere in this regime where we're observing. And so we're going to be able to determine, because we have instruments that are matched by design, we're going to be able to determine where the differences across the gap indicate a fundamental turbulence onset or whether it's instrumental. We know, again, this is again looping back to how the remote sensing versus the in situ. We know that when we measure the solar wind at the Earth, that there's small structure everywhere. And we don't really know if this is small structure that originated way back in the corona or structure that formed as it moved in the solar wind, as the solar wind evolved. That's what Punch is going to be looking at. The third ambient solar wind science goal that we have is to identify the mysterious Alphane zone. The Alphane zone represents the height at which the magnetic field of the solar wind, the Alphane speed associated with it, becomes smaller than the outward solar wind flow. And I remember when I was a graduate student, people talked about the Alphane point, which was an actual, like a solar radius, at which point this happened. Well, as we started getting nice global models like are shown here, people started talking about an Alphane surface, because of course, the place where the magnetic field versus the solar wind flow is going to depend if you're in a fast wind, if you're in a slow wind, if you're in the weaker or the stronger field. And as this nice simulation shows, it's going to depend on where you are in the solar cycle. On the left, you're seeing the pink is showing you in this model where the Alphane surface would be for the solar minimum, and here where it would be for solar maximum. But as we start to look at some of these observations from Core 2, for example, we realize that it's even more complicated than that. And the reason is the Alphane speed also depends on the density. And so that riotous torrent that we're seeing flowing at all time means that we probably have a fractal zone rather than a true smooth surface that is the Alphane zone. Punch is going to go after this. It doesn't have to measure magnetic field, and the reason why is because above the Alfvén zone, the plasma is propagating outwards. The solar wind is disconnected from its source at the sun. Below, motion in both directions is possible. And this is basically easiest understood in terms of frames of reference. If you are in the frame of reference that's moving with the solar wind, you'll have waves moving in both directions. But from the observer's point of view, once the solar wind dominates, you no longer have anything moving backwards. And so it has been attempted to do an analysis like this with Core 2, and that's what's being shown here. And it was basically, there was structured inbound flow everywhere that was observable, which tells us that the Alfvén zone, at least to some extent, has to be above these heights, which are about 12 to 15 solar radius. So Punch is going to be able to make these observations above that range. And so we essentially have a lower limit of about 15 solar radius for a streamer and 12 solar radius for a coronal hole. And here's where we find complementarity to Parker Solar Probe, because again, Parker Solar Probe is going to be flying into these distances from the sun and measuring in situ the magnetic field, the density, the velocity, and getting the ground truth of the Alfvén velocities versus the solar wind velocities, which then can be brought together with the Punch remote sensing observations and the global view, which is what Punch is bringing. So now let me get to the second main objective, which is the dynamic solar wind. And here we have three questions. First of all, coronal mass ejections. We want to understand their 3D trajectory, structure, and evolution. Second, co-rotating interaction regions. These are the regions where fast wind catches up with slow wind. And related to both, shocks, their 3D dynamics, and their morphology. So let me start with CMEs. Well, we know that coronal mass ejections are quite complex, even back at the sun. We know that they have interior structure that evolves and changes. That CMEs may be deflected. They may rotate. This is a nice movie. I'm going to show it a couple of times. If you watch just here, go back and show it. Even close into the sun, there's evidence that the coronal mass ejection may rotate. This can cause all sorts of issues if you're trying to, for example, predict what the direction of the magnetic field is at the Earth. If you take a source region at the sun and you get a nice idea of what the magnetic field might be, if things change quite a bit en route, then your prediction is going to have troubles. Also, there's substructure. There's interesting substructure, and this is somewhere where Parker Solar Probe, there's an interesting complementarity, because Parker Solar Probe is doing heliospheric imaging right up close to the sun and is observing little tiny flux ropes everywhere, not just the big ones that make the large CME, but these little puffs that have been seen in the solar wind. There's evidence that these all might be little magnetic flux ropes. And so Punch is going to provide the global context for this because it has 10 times higher sensitivity than any coronagraph of this nature before. The other thing is, and I'll get to this again in a moment, Punch has polarization at all heights. We've seen polarized brightness in coronagraphs, but to date we have not had polarized brightness in heliospheric imagers. And the reason that polarized brightness is important is because polarized brightness, when taken in combination with brightness, can help you localize the structure of the plasma that you are observing along the line of sight. And so Punch is going to be able to pinpoint these structures and watch their evolution between the sun and the Earth. The second, and I'll get back to the polarization again in a moment. The second main target is co-rotating interaction regions. And here's something where this is a model, and at the moment this is the only way we can have these nice views. This is the polar view. We'd need a polar telescope to get this in observations. But with this polar view, what you're seeing is fast solar wind catching up with slow solar wind, and you get this spiral type structure. This is the Enlil model at the CCMC, and these are planets, and so you can see the structure and what you would expect to be crossing the various spacecraft and planets. So this is the view from the poles above the sun, and then this is the view, for example, from the Earth. And you can see it looks very different. You just kind of get this blob coming out. And this is another view. But these are the two that I really want you to focus on. Now, co-rotating interaction region, we're interested in their formation because we're interested in how that fast wind and slow wind come together. And this is important because that is critical to how you predict the angle and impact time of this structure as it hits the Earth. There's also shocks that form. And finally, there's expectation that there are waves that are launched near the source region as the pilot begins, but the measurements are sparse, and the sensitivity has really been a restriction for this. So what Punch is going to do, it's going to have the sensitivity, but it's also going to have a wide field of view, which is really quite unique. That full vision of the entire, the sun going at all latitudes. And the reason this is important is because it can observe the CIR, co-rotating interaction region, both in its manifestation when it's late, far from the sun, and close in, near to the sun. So this structure is going to rotate past, and so you'll be able to observe different aspects of the same co-rotating interaction region with Punch. And then there's shocks, which may form with the CMEs, but also with the co-rotating interaction regions. Simulations, again, a lot of what we know so far is really informed by simulations, and these suggest that the CMEs are strongly affected by turbulent instabilities across their fronts, and that there may be these sort of corrugations in the shock fronts. And the resolution, by the word that the word that I was trying to find earlier was resolution, spatial resolution. Don't know why that one went away. But the high spatial resolution that Punch enables allows you to look at, for example, the turbulence and the shock fronts, the corrugations. The current generation of chronographs and heliospheric imagers are not designed to capture this evolution. And they're very, we also need high cadence because there's a blurring that happens that can be processed if you have enough, if you have a high enough cadence, which Punch does. So Punch has, this is where the cross-scale part of the problem comes in, because Punch has this global view of shock structure, but it also has the sensitivity to resolve these interfaces to look at the turbulent interactions. Which brings me to polarization. And this is essentially, it's basically just geometry. What we have is we have polarized light, and there's a scattering direction. And the scattering direction, chi, can be directly related to the ratio of polarized brightness of the visible feature and the brightness. And so these are observable quantities, polarized brightness and brightness, if you have a polarized imager, which Punch does at all the heights. And from that, then you can get this angle, and then it comes down to geometry and angles and laws of sines and cosines and so on. And from this, you can find that that you can get a full 3D position of an element along your line of sight. You've got your sky plane projection to give you your YZ, and your X, which is along your line of sight, can be obtained by this fundamental measurement of polarization. And proof of concept has been done to see how you would use this, because of course you're looking at an optically thin plasma, so you're going to have material all the way along your line of sight. So what you're going to actually get out of this is some sort of weighted mean of the structure that's along your line of sight. If you're looking at a CME, however, it will be the weighted mean of the CME structure as it passes, which is what you want to know, the 3D position of the substructures within it. And so this has been tested, again, with the stereo core 2 observations. And in this case, what was done was that the stereo core 2, which had polarized brightness and brightness, a substructure, which is seen here in the stereo A view, within this CME, the location along the line of sight was determined. And this image shows what happens if you rotate it around to the SOHO view. So this green points then become this green blob, which is in here. So it basically, and that would only work if you basically got the 3D structure right, because you're taking a structure that you're observing from one view and you're seeing where it would appear in the image of the other. And perhaps more compelling, what was done with this particular structure was a measurement of the chirality, the direction of the twist, because this kind of light bulb structure is often modeled as a flux rope. And if this is the axis of the flux rope, then it could either be a right-handed or a left-handed twist around the center of the flux rope. And the way you can tell the difference is if you see this green structure not just as a little backward C, but if you know what's foreground and what's background, it tells you what the chirality is. And that's what they did with this. And then they showed, in this particular case, because it was a case with nice stereo and SOHO observations, and so it intersected a spacecraft, that they got the sign of the chirality correct. that the magnetic flux rope that passed the spacecraft later was in fact the right direction. Now, I can be skeptical about these things because, you only need to get things wrong twice to get them right. But, so I wanted to look at this from a slightly different angle instead of the observations, because what you want to do, and what Punch will do, is to do this analysis over and over and over again in order to really pin down how well this method works. So I took the forward modeling approach and said, well, if I have a simulation, in this case was a simulation of Yuheng Fans, of an erupting flux rope, and I forward model what you would expect to see in white light, polarized brightness and brightness, and then I pretend it's real observations and analyze it like Punch will I get the right sign of the chirality? And I was very happy to find out that I did. And so what this shows is this is the simulation density. So you can see there's a bright core structure, which is the core of the flux rope. This is the ground truth. It's a simulation, so you know the answer going in, what's in the foreground, what's in the background, where you have red is front and blue is back. And so this is a structure which is a left-handed flux rope, okay? And so taking this structure, we then took the polarized brightness and the brightness, and we tracked the feature, and we said, what would the expected distance be along the line of sight from the plane of sky? And you can see the red is red and the blue is blue, and it matches up quite nicely. And here's the key. The circulation about the axis going from blue to red correctly identifies it as a left-handed flux rope. So this is a tremendous new tool that we're going to have with Punch to be able to observe. And this is a place where I see a wonderful connection to Aditya and to the VELC and to what can be observed in terms of the linear polarization and the magnetic fields back at the sun. And so to conclude, Punch is going to do multiple things, and we're going to be putting these data out for the community to use. The daily global solar wind maps, which can be used in all sorts of studies. Looking at the onset of turbulence as the solar wind forms in the outer corona inner heliosphere, observing this uncharted Alphane zone and seeing how it changes with time, tracking the CME's substructure and chirality, looking at both the CIR formation and evolution, and then characterizing the cross-scale shock dynamics. And I'm going to conclude and actually let this run while I get questions, because it's a super cool movie, with a movie which is going to show the launch sequence of Punch. I'll run it a couple of times just for fun. See if I can get it to start. And so, I don't know. There it goes. Okay, thank you very much.
Yeah, thank you I'm happy to hear your talk. Yeah. So the resolution, you said 10 times more resolution increased through the polarization observation.
Sensitivity, 10 times more sensitivity, yeah.
So how you improve the sensitivity?
Just essentially new advances and yeah, I mean, I'm sorry, I don't have a good answer to that.
You use some polarization camera or the polarizer? You rotate the polarizer or use the polarization camera?
I'm afraid I'm going to have to punt on some of the details of the instruments and talk to you and get you information and answer during the break because I don't have that at my fingertips.
I don't know. Yeah, here. Yeah. No, here.
Very good. So you mentioned that Punch studies Alphane zone, and you showed some plots of Alphane surface during the solar maxima and minima. And apart from that change during the cycle, at a time when due to irregularity of solar wind, for example, when a CME passes, will it not change its position? Are there some theoretical estimates at least how much the Alphane zone may shift back and forth when something like a CME passes or other disturbances?
Yes, absolutely. I mean, you would expect that. And even without the CME, I mean, I think that's what we're starting to wrap our heads around with this this movie here. There's structure passing through at all times. And so how is this going to affect the alphane zone is something which we're going to have to study and see the observations. The models are fantastic, but they tend to be much more smooth, right? They tend to be, you know, a much more smooth type model. So we can learn something from that. But I think in this case, the observations are going to have to lead the analysis in understanding how the structure is impacting the alphane zone.
Sir, I was wondering if you could actually put in these observations of the chirality that you measure from the polarization, along with the underlying models of the flux slope, and actually infer the flux slope topology, kind of in an inverse problem. I think this should be in principle possible from the measurements.
Yeah, so for example, if you have observations back at the sun, you have observations of the magnetic boundary condition, you have observations especially of the coronal polarimetric measurements and everything else, and you come up with your best model of the CME pre-eruption and then during the eruption. Punch is providing information about how that is changing as you continue to move through the heliosphere. And it's providing a sort of a ground truth, I won't call it a ground truth, but it's providing another test of what your model assumptions that have gone into that flux rope, which quite frankly are under constraint right now.
There's a question at the back.
Sarah, this you are measuring shock. How do you identify the shock? Is it just the enhancement in intensity, which is basically the concentration of electrons, or how do you?
The shock, you're asking about the shock, for example, the corrugations. Yes, it's going to be electron density is what we're going to be observing.
Yeah, but you know, it has to be, if it is in a different perspective, if you edge on see, then it may not be a little region where the electron concentration will be more, so.
That's true, and so we're going to have to observe multiple cases, and as in so many things in solar physics and heliospheric physics, we're going to hope for the one at the right angle, which is going to give us the structure that we want to see. But we spec'd out our requirements based on the time and the duration and the expected number of CMEs and so on. And we are confident that we're going to see something.
But there is no way to measure the velocity at that region.
Well, we can observe the structure as it moves and get a flow map of it, for example. And with some information about its location along the line of sight, we get a better idea of its trajectory, for example, as well.
So, any other questions? Yeah, there's one.
I'm a bit interested in the turbulence in the ambient solar wind. So, if you observe it in polarized brightness, in that case, you basically observe the density fluctuation, right? So it's compressible turbulence. So a bit different from the usual standard incompressible turbulence. Do you think these two turbulence is completely different, or?
Sorry, I lost the very last thing you said.
So the observed turbulence is a compressible one. So I want to know the connection between the standard incompressible turbulence and the observed turbulence.
Yeah, I mean, we're seeing essentially a spatial structure and a change in that with time and space. And the analysis of that and the comparison of that to what's being observed in situ in the solar wind, where you can measure the turbulence more directly, is what's going to have to happen after that. It's going to be fascinating, for example, to look at what Parker is observing quite low down and what's observed at the solar wind at the Earth, for example, in situ, and to put this into the global context that Punch is going to provide.
Okay, so let's thank Sarah once again. Now I invite Laurent Dola. Okay. So Laura, I will show at 20 minutes the 5-minute mark. So that 5 more minutes for questions.
Do you hear me? Yeah? Oh, I know. Okay, I had plugged my... Okay. Okay, so I'm gonna talk about the proba-free Aspix coronagraph, which I will present now in more details after I present the proba mission. So the proba mission is an ESA technology and an ESA technology demonstration and a mission of opportunity in the ESA science program. So both, and it's composed of 2 spacecraft in flight formation. So you have here the 2 spacecraft to achieve an artificial solar eclipse. The launch is foreseen at the end of 2021. And it has a 2-year lifetime, and it's not like we say usually it has a 2-year lifetime and then it can be extended. It can be extended only if we have enough fuel, because of course to maintain the formation flight we will use fuel, and depending on how much fuel will be left at the end of the 2 years, we will know how much we can extend. The proba-free orbit is a highly elliptic. It has a duration of about 20 hours, and the formation flying will be achieved about twice a week on average. I will come back later to that. And it will last around 6 hours at the apogee, where the spacecraft, the relative velocities of the spacecraft are the smallest. Now the 2 instruments that are part of the scientific payload, so Aspix, the giant coronagraph here, which is led by Royal Observatory of Belgium, and the PI is Andrei Zhukov. The telescope will be placed on the bigger spacecraft, and the external occulter will be on the smaller spacecraft, 144 meters apart. And on this external occulter spacecraft, on the side that is facing the sun all the time, there will be the DARA instrument, which is a solar irradiance monitor. The PI is Werner Schmutz from PMOD in Switzerland. And now I will present more the proba-free coronagraph in which I take part. So first, the field of view. So basically, it starts from 1.097 to 3 solar radii, and of course, a little bit more in the corners. We will have a 2048 by 2048 pixel detector, and the resolution is about, half the resolution is about 2.8 arcsecond per pixel. The positioning of the external occulter here is a technological challenge, because the distance between the spacecraft, as I told you, is 144 meters, and the accuracy of their 3-axis positioning should be a few millimeters. So both into the distance to the spacecraft and also in the relative position towards the optical axis and the sun, spacecraft sun axis. Aspix will be, there is already a flight model, is a classical LEO coronagraph. So basically, there is an external occulter here that stops most of the light from the solar disk. There is anyway some scatter at the edges of this external occulter, which is stopped, blocked by an internal occulter on the field lens here. And because there is also diffraction at the entrance aperture, we stop it with the LEO stop before the relay lenses, and then we have the filter here before the detector plane. There will be a very low stray light level. hopefully. But in theory, we can achieve this level of stray light which at the center of the entrance pupil in comparison with existing coronagraph. And because we have such low level of stray light, we can put the inner field of view very close to the solar limb, and that's why we can have it at 1.097 solar radii instead of the 2.2 of LASCO for LASCO, which has, let's say, similar level of stray light. And if we have a lower level of stray light, of course, we can better see the small-scale structures, and because we have a better contrast. A bit more about the stray light analysis that we have, the team has performed. So this figure here shows in gray the total of the light that we expect, both from the corona and the stray light, the instrumental stray light. So you see that it is very close to the red one, which is the corona alone. A large part of this component is only near the solar limb, at close to the edge of the external occulter, and is due to the diffraction on the external occulter. And then we have also computed the ghosts and different scatters characteristics due to the optics, due to the, in particular, to the lenses. We have also computed state-of-the-art diffraction calculations that allowed us to make an analysis of different conditions of misalignment. So the first figure here shows you the ring of stray light around the external occulter for a perfectly aligned system. If there is a little bit of a shift of one of the external occulter compared to the optical axis, then we have, I hope you better see than me, we have a very little variation. If we have a tilt, this is where we have the most impact. If we have a tilt of the Coronagraph spacecraft with its optical axis compared to the Sun external occulter and Coronagraph spacecraft axis, sorry, then we have, you see here, this slight asymmetry, which can get worse if we increase the size of the tilt. So those are for a tilt of 10 arcsecond and 25 arcsecond. We have 6 different channels. The filter wheel makes it possible to observe only one channel at a time, but we can move the filter wheel in less than 1.5 seconds. And now I can tell you more about those filters. We have 4 versions of a wideband filter here, which is centered at this wavelength, so it's kind of a greenish color, with a full width at half maximum of about 30 nanometers. And in the different versions, we add a polarizer with a different degree so that we can make polarization degree measurement and polarization direction measurement. Then we have 2 narrowband filters, one for centered at the green line of iron 14, so kind of a hot corona, with a very small full width at half maximum of the passband, and also the helium-1 D3 line, which is more for the observation of prominences, which is a slightly larger full width at half maximum, because the line is a bit bigger, and we can allow also more contamination from the continuum, because our purpose is to make linear combinations of the measurement in the wideband filter and the narrowband filter so that we can subtract the continuum contribution and really tell what is the contribution of the spectral line. Because, in fact, in the case of the green line filter, most of the time, 50% of the photons will come, even though we have a very small full width at that maximum, most of the time, a large part of the photons will come from the continuum. A bit more illustration of those passbands. So here you have the green line filter, the wideband filter, and then the D-free filter. With overplotted the different synthetic spectra of the corona as we expected in coronal holes, streamers, and denser streamers, so for different temperatures and densities. And so you see that, okay, maybe let's go directly to the zoom. You see that clearly we are targeting at iron 14 here. Here I didn't show it because it's a coronal spectrum, but we target the helium-1 line. There will be a little bit of argon-10 here, but that's really negligible. And a little bit of calcium-15 also. You don't see it, but it appears here for very hot plasma. There is a second calcium-15 line here. But if the plasma is not too hot, it should be in a small amount. Now, if you want more comparison with other coronagraphs, so here we compare the field of views. Here we compare the vignetic function. So you clearly see that we go much closer to the sun, and we have a very little zone on which the PSF will be degraded, and of course the intensity also is degraded. And also the spatial resolution here in comparison with the other coronagraph. So I can give more details about that if you want, but now I move to the science objectives. So if I could summarize the science objectives, I would say is to fill the gap between the field of view of current coronagraphs and current EUV imagers. So here you have an SDO images, which is below 1.227 solar radii only, and then you have the LASCO image, which starts at 2.2 solar radii. So in between, you have a gap. And unfortunately, in this gap, we have the solar wind that starts to become supersonic. We have also the peak acceleration of many CMEs. And it is also the crucial transition between the closed field regions, where the magnetic field is dominating, and the open field regions, which, where the solar wind is dominating. And of course, there will be a solar orbiter soon and the METIS coronagraph, but even at the closest approach, we still don't completely fill the gap. And ASPIX will get even closer inside the field of view of SDO or SWAP on board Proba 2 and other UV imagers. So more details about the science objectives of ASPIX. So first, the quiet corona, and second, the active corona. So very classical. So for the quiet corona, in particular, we are interested in the structure of the magnetized solar corona. So for example, here, when we have models like this one from predictive science, we would like to compare them with observations and compare if the field lines superpose with the structures that we see in the corona. We want also to observe the fine structure, the dynamics, and the waves of, okay, but here it's a bit, but no, the waves are in the quiet corona, yes. For me, it's part of the quiet corona, the waves. Then second batch of science objectives is the source of the solar wind. In particular, there are many competing processes that are proposed to explain how the solar wind forms. Most of them, they are kind of interchangeable connection, but with slight differences. And those the differences, they occur inside the gap again. So that's where ASPIC will make some improvement. Now about the active corona, so mainly the CMEs and the shock. Mainly the shocks associated, sorry, excuse me, the shocks associated with the CMEs. So we want to measure the CME kinematics in the inner corona, so again in this gap. And we want to observe in detail the full coronal restructuring during the CMEs. So again, what happens here in the gap when the foot points of the CME evolves and the solar corona restructure. And of course, you can notice here on this composite image that with EUV images, we see the CME here, we see it in LASCO here, and we see that can be an EIT wave also, part of what you see here. But we observe the radio emission at the shock, but with a very bad resolution, of course, and we have again the gap, and that's where ASPIX hopefully will bring more details. The science activity plan. So the Science Operations Center will be located at the Royal Observatory of Belgium, so that's where we will send the commands that will be further transferred to the spacecraft. That's where we will write the programs. And that's where also we will collect the data and process them to make them available to the community with an open policy for the data. When I started to write the science activity plan, the official document, it was supposed to be for launch on end of 2019. And at that time, so we expected that the first part of the mission would be still in the slow part of the solar minimum, and then progressively the activity would increase. So the smart way of doing that was to say the first year would be devoted to observation of the quiet corona, and then the second year would be more devoted to something more operationally constraining, which is for CMEs, etc. And now we have progressively shifted. I told you the launch is foreseen at the moment for end 21. So I suspect that now we will more have a mix of quiet corona and active corona during the 2 years, depending on the condition of the suns, on the sun. Another important point to notice is also that because of the high dynamic range of the brightness of the corona, we cannot register the full field of view up to 3 solar radii in one exposure. There will be saturation or exposure in part of the field of view. So we have 2 to 3 exposures for the same scene for a given channel. So they are transferred to the ground, most of the time only partially, using tile maps. So we can determine a tile map on the detector to say we want only those tiles to be downloaded for this part of, for this exposure. So we can focus on the well-exposed part for each exposure. And then we will recombine them on the ground. Another point related to this science activity plan is that the coronagraphy orbit, the formation flight orbits, will be run about twice a week over the 2-year nominal mission. So this is a compromise between the total fuel that is allocated and also the telemetry, because there is no point in making a lot of observations if we overfill the memory and we don't have time to download everything. So, but this 2 per week formation flight is adaptable, flexible. We can adapt it depending on the activity on the sun, and if we have, we want to run programs that will take a lot of weeks to be downloaded, for example, for the data to be downloaded, so we can, of course, adapt that. As I told you, we have an onboard memory, which is 88 gigabits. We can download roughly 30 gigabits per week. So, of course, we have some margin, but the problem is that there are some of the programs that I will detail later that may take a lot of, observe a lot of data at once. And something important is that we have a guest investigator program that is planned to, like it was for Proba 2, for the people that know the Proba 2 program. So to both involve non-co-investigators in the choice of the observations and also to provide them with the expertise, thank you, with the expertise for the data analysis of the instrument. So it is foreseen that about 10% of the observation time and telemetry will be devoted to those GIs. So we have at the moment a minimal set of 4 observation programs to match as many science objectives as possible with a little bit. So the full set is basically all the filters, all the exposures, but at the beginning and end of each orbit for long-term analysis of the evolution of the corona. Then we have the synoptic, the so-called synoptic, which contains the full set every hour in addition to the beginning and end, and only the white light, the wideband filter at 6-second cadence. Then we can do something more intense in terms of cadence. So again, only one filter, the wideband, but also the narrow bands if you want, at 2, 4, and 15-second cadence. But that's only for indication at the moment. It's by adapting the number of exposures, of course. And we have to reduce, in fact, the field of view to 1/4 of the detector to compromise with the readout and the telemetry volume. And to finish with the most important one, I think, the most difficult one will be the CME watch, because we want all the filters, the wideband and the narrowband filters, with an exposure time of, with a cadence of 30 seconds, the polarization every 5 minutes, and that will produce more telemetry in 6 hours of the coronagraphy orbit that can be downloaded in 1 week. So we have designed a selective downlink scheme to identify and download only the events, so only the CMEs. If there is a CME of during 2 hours, for example, we will identify which time interval it is, and we will download only the data during those 2 hours, but at maximum cadence of 30 seconds. Of course, we plan to have synergies with other missions like Solar Orbiter, Solar Probe, and Aditya. First, the multi-view point observations, the complement to the analysis of magnetic connectivity. So this is quite classical, but this is one of the main objectives of Solar Orbiter, for example, and Parker Solar Probe. Also for cross-calibration, for METIS there will be also white light, so we can cross-correlate. In particular, we are interested in the green line filter of Aditya for cross-calibration. And also the other instrument, they can help us determine this time interval where we have a very interesting event to download the data only on this event, in addition to our own system of quick look data. Of course, we can have synergies with the radio ground facilities for the studies of shocks, and the solar eclipse. There is one solar eclipse which will occur at the beginning of the currently planned mission, and which is again a good opportunity for calibrations. So to conclude, I would say that PROBA3 is a mission of ESA that is driven by both science and technology. The main scientific payload of PROBA3 is the ASPIX solar coronagraph. Due to the unique separation between the telescope and the external occulter, 140 meters, PROBA3 ASPIX will be able to observe the inner corona as close to the center as 1.097 solar radii in low stray-like conditions. That's our best point. And ASPIX will fill the gap between the low corona, typically observed by DUV imagers, and the high corona, typically observed by the externally occulted coronagraph. And PROBA3 is on the way to be launched in the end of 21. So yeah, a priori, we can have joint observations with the Solar Orbiter, Solar Probe, and also Aditya. Thank you. Yes, thank you.
Thank you, Laurent. So I think Shankar missed to highlight the PROBA3 and Aditya's overlap very much, because we are looking at exactly the same field of view. So it will be very important to have joint observations. Particularly, you have a very small window of observation, so those periods we should be having our observing programs absolutely co-temporal. My question was about the filter bandwidth of the continuum channel. It seems you have a pretty large filter bandwidth. When we did the calculations in terms of continuum, you also have a CMOS detector, right?
Yes.
So because of the low shell capacity, so in our case we had to really reduce the bandwidth of the continuum channel, because of the counts. So,
I would say in our case, it's the reverse. We would have preferred to make it larger.
Yeah, so you had to reduce it. So what is the exposure time you're aiming at?
Typically 0.1, 1, and 10. But because we had to add a neutral density filter in the optical layout, we will probably have to increase those exposure times. But roughly, yeah, 1 second and 10 seconds.
Yeah, we are not able to give in. So you have a good ND filter, which we do not have in the continuum channel, if I recall. Maybe we should discuss it at that, because in our calculations, we restricted it to only, few angstrom for the continuum channel.
And in fact, we decided on the width of each channel on purpose to avoid bright lines. In fact, the width is driven by the presence of the lines on the edges. So we wanted to reject them to lower than 1%.
Yeah, yeah. Okay. Yeah.
If there are no more questions, let's thank Laurent.
Thank you.
There is a question, sir. Yeah.
Maybe I missed, but I have a question.
Excuse me.
Maybe I missed what is the orbit of the satellite, and how do you keep the two satellites distance, 144 meters?
So the orbit of the satellite is from 600 kilometers to 60,000 kilometers, because it's highly eccentric. And when it is at this 60,000 kilometers, they will be brought together to 144 meters. But the rest of the time, the satellites are put in a safe configuration so that they don't collide. There is no risk of collision.
So what is the percentage of the time?
It's 6 hours out of 20 hours. So
6 hours out of 20.
1/3, let's say.
Okay, thank you.
Okay, so let's invite Andreas for
yes,
talk.
Of course. Thank you.
So, before, is it working? Hello? Is the microphone working? I can't. Okay. So before we go to the lunch break, I would like to introduce you to the Sunrise project. And I want to discuss in this talk a few things. The goal of the talk will be that I want to explain you what Sunrise is, what we achieved with the previous 2 flights of the Sunrise Observatory, and why we want to do a 3rd flight. And this question, why we want to do a 3rd flight, is of course a central one. We made the decision to fly again, despite the fact that we know that high-resolution observations are now also possible, or even better, to be done from the ground, what was demonstrated recently by the DKIST first light images. We also have established a science working group which will prepare the Sunrise 3 science. It's very important that we get input from you, from the community, to also define science projects like you did for the DKIST critical science plan. We want to do the same thing for the Sunrise telescope, to be prepared optimally for the new flight. We have the representatives here. The science working group is led by Smitha Narayana-Murthy at the moment at MPS, and we have contributors from all COI institutes. But now first I want to introduce you a bit what Sunrise really is. And we heard nice talks about especially observing the corona, and now I want to talk about what sunrise will do in terms of observing the photosphere. And there are several ways you can observe the sun. I mean, of course, you have the full disk approach, like what is done with HMI, but for sunrise, we decided to really go to the highest resolution possible, and that is indicated by this small field of view here. This is what we will cover with sunrise, and that's where we have to get the information from. Sunrise 1 and 2 was very successful, and here I show the main data product we achieved with the first 2 flights. The first image shows over a range of 30 megameters just a continuum intensity, representing also the temperature of the optical surface. We had instruments which allowed us to observe the chromosphere. Here are 2 calcium narrowband images where you can see the fibrous structure of the chromospheric, the fibers covering the photosphere in the chromospheric height. And we had a spectropolarimeter on board, IMAX, which obtained the information about temperature, height stratification of the temperature, but also magnetic field strength and direction and line of sight velocities. That was done using a stratospheric balloon, and the stratospheric balloon was now flown twice. And here you see the 2 trajectories. The launch is always in Kiruna, North Sweden, and the circumpolar winds let this balloon float towards the Canadian soil, where then the balloon is cut and the payload, the Sunrise Observatory, descends on a parachute. How this looks like when you are on board of the Sunrise Observatory is illustrated in this movie. There you see, there you should see, if the movie works, that the obviously doesn't play. Now it does. We see how the telescope follows the sun, and also a very important fact is that you see also how dark the sky really is. It's really a very dark sky. The sun never sets. We have very long time series possible, but you also see already the challenges to stabilize this platform, to really have the accuracy and the stable pointing of 0.01 arc seconds. There were 2 flights already, as I mentioned, and these 2 flights resulted in more than 100 refereed publications so far. And these publications were summarized in an overview publication by Sami Solanki in 2017, where he highlighted these sunrise publications. And in the first flight, we had many discoveries. Since we were the first telescope to observe at this high resolution, it was easy to discover new things. So the first papers had many firsts and discoveries in their titles. The second flight was equally successful. There we had the possibility to also observe active regions, which was not possible during the first flight because the sun was absolutely quiet then. And there we have also a lot of new discoveries, mainly about then more active regions and wave analysis. I want to highlight 2 things we did with sunrise. Here is one publication, which was a very easy one, where we discovered for the first time where we could resolve these kilogauss flux tubes in the quiet sun. So here you see the magnetic field strength over a field of view of about 6 times 5 megameter, and for the first time we were able to infer the magnetic field strength of these magnetic flux concentrations in the quiet sun directly without any filling factor techniques. So that was one of the highlights of the first flight. The second flight I already mentioned. There we concentrated also on the analysis of active regions and of the chromospheric features there. And I want to highlight here one study done by 2 PhD students at MPS. And what they did, they looked at this calcium image. Here you see this sunrise calcium image. And they looked at the temporal evolution. Here you see a space-time image. So the time is moving, it is going in this direction. And then this artificial slit moves over the image to makes you see what appears in this time-sliced images. And I want to point out, this is the contrast-enhanced version of this image, and there you nicely see this oscillatory behavior of these calcium fibrils. And Shahin Shafarzadeh was able to deduce from this the type of the waves. He discovered that these are transverse waves, transverse observations, which carry enough amount of energy to heat the chromosphere and also the corona. In another study of another PhD student, Ricardo Gafera, he found, using the same images, a different type of waves. He looked at the intensity fluctuations at the loop top of these waves, of these fibrils, and he found these pulsations here where time is running up, and you see how the intensity varies, and you clearly see that this is like a sausage mode wave, and that was also identified as a sausage mode. And also there, it was the uniqueness of sunrise which enabled us to do this, use this stable observatory platform to detect those waves. So we decided to submit a proposal for the reflight. The plan was to fly in 2020. In the meantime, we shifted the launch date and fixed it to 2022. The question is, of course, why should we do Sunrise 3? Why should we fly again? And the question is a very valid one, now that we see how well we can observe the solar surface in high resolution also from the ground. In the meantime, we have very fast cameras. These fast cameras allow for powerful image reconstruction techniques. We have sophisticated instrumentation attached to those telescopes. And of course, the size of the telescopes are now is much larger. So this is now from the DKIST first light press release of last week. You see how really fine structured things are on the sun and how well DKIST is performing and recovering these fine structure. With sunrise, the resolution will not be much different from this one. This image was recorded at 790 nanometers. At sunrise, we have half the wavelength. That image is not yet at the diffraction limit. So at 400 nanometers, it corresponds approximately this resolution we will also achieve with sunrise then. But not quite. So the resolution is not the argument for flying sunrise again. But there are several other reasons, and one good reason is that if we go up above the atmosphere, then we don't have any atmospheric dispersion. We can combine measurements at different wavelengths simply because the light is not changing direction to the diffraction in the Earth's atmosphere. You see an indication how big this diffraction is. If you look at the near infrared and in the infrared, then you see that you have, if you observe really a small scale feature, almost no overlap. We can have very long and constant quality time series simply because we don't have any seeing and conditions are very stable, and also we can go beyond the limit of ground-based telescopes, which usually, if it's a very good observation campaign, you might have a duration of 2 hours, 3 hours. We have no restriction. We can even observe 24 hours and longer. The most important thing is that we have access to wavelength we cannot access from ground. So the near UV range is one of the focus of our scientific analysis. We have the seeing-free environment. This makes us also very strong when we apply the same techniques as you do for the ground-based telescopes, the image reconstruction techniques. We don't have to do it with the same level of aggression, so we have we maintain better the signal-to-noise ratio of our data. We have no telluric lines, gives us access to spectral lines which are not observable from ground, even in the visible. And also an important point is the sky brightness. If you look at this plot here, you see the sky brightness over wavelength, and the two red lines indicate for 40 kilometers height the lower ones line and 30 kilometer height the upper red line. Good daytime seeing is indicated by these 3 purple crosses. So with sunrise we have sky brightness which is more than a factor of 2 lower than what you factor of 100 lower 10 to the power of 2, lower than what you can get from the ground. The biggest advantage we want to benefit from is that we can observe in the ultraviolet. Here's an example which is not really in the ultraviolet yet. It's about 400 nanometers. We did that because we wanted to compare it with observations we obtained. And the interesting thing about this region is that there are many, many spectral lines. And these many spectral lines, with sunrise, we can observe them always exactly simultaneously because of the lack of atmospheric refraction. We really look at the same spot on the sun. And if you look at the intensity spectrum, Stokes V and Stokes Q signal, you see how strong the signals are and how diverse the information is we get from those lines. And if you look at a spectral region of about 30 angstrom, that's what we will cover with sunrise in one shot, then these spectral lines are formed at very different heights. So here's a plot where you see the formation height of spectral lines, typical formation height over this near UV range where we want to observe. And you see that you have a very high density of spectral lines, and you will cover the from deep photospheric level up to the chromosphere, you will cover all the heights. The same approach is also there when we do observations in the near infrared with another instrument. I will describe the instrument a bit later. And there also the goal is to really get the coupling from the photospheric height using several spectral lines up to the chromospheric height. The near UV range offers also very powerful techniques to observe very weak magnetic fields. So the near UV, there we have very strong scattering polarization signals of many spectral lines. And these signals are very strong, and we can, with sunrise, not only detect these signals like it was done in the atlas by Achim Gandorfer, but we can also retrieve the information because we can spatially resolve these scattering polarization sources. So to combine, to summarize, we really benefit mutually from having a high-resolution telescope like DKIST on the ground and sunrise as an observatory flying for 1 week. We can outperform DKIST in many points, like the high resolution, magnetic sensitivity, and especially here, long-term stability, atmospheric stray light, and near UV exploration. I would like to emphasize 2 or 3 not so obvious points which are important for sunrise science. And I want to go back to this plot here where you see the highly corrugated formation height of several spectral lines. And the problem is, if you want to obtain physical parameter maps, then you always get these maps at these corrugated surfaces. And one very difficult point is how to get from these corrugated surfaces to really geometrical XYZ plane. And how difficult that is, Shibo Matthew knows that. He did important work in 2004 for the Wilson depression in sunspots. And here we have an image of a later work where it was investigated using an MHD simulation. You see that the change in height, here's the height and here's the cut through the sunspot, the change in height can happen very rapidly over several hundred kilometers over only a few pixels. And this is making it very difficult for methods which convert from optical depth scale to geometrical scale. You then lack the information to really couple these pixels together. With sunrise, we will have this possibility because we will cover so many spectral lines simultaneously that we have a full coverage from all height layers, and we will be able to obtain parameter maps also on geometrical height scale. And that allows us to, for example, look at power spectra. Here, there's I think one of the best observed power spectrum of the magnetic energy density. And this was done by Sanja Danilovic, and she used Hinode data and to obtain those power spectra. And in order to compare the power spectra with observations, you only have the possibility to degrade the observations. And that's what Sanja Danilovic did. She degraded the simulations And in the end, she found some kind of agreement between observations and simulations. But of course, the power spectrum itself doesn't look at all as the power spectrum, as the magnetic energy power spectrum should look like. And with sunrise and doing the observations in a geometrical height scale, we might be able to come much closer to a real power spectrum, and the comparison with observations with simulations will be simplified significantly. Another important thing is that sunrise offers the stability to do wave studies. Wave studies rely on very stable platforms because there you want to avoid to have fluctuations from seeing, from atmospheric turbulences. You really want to make sure that the fluctuations you observe are really solar features. And that's why sunrise being above these seeing affected atmosphere, there you can do these wave studies with accuracy which is not achievable from the ground. And you need for that the high spatial resolution to discover the kink mode and sausage mode, for example, but also you need the high magnetic sensitivity to, for example, get details from Alfvén waves. We need a high temporal cadence, we need high stability, and we need, again, the height coverage to be able to get the waves from the photosphere and how they propagate to the chromosphere. Another thing I want to mention is that also in terms of this fundamental physics we can achieve with sunrise, there's also the topic about measuring the helicity. And in a work by Nishant Singh, he showed that these helicities, according to dynamo theories, you should always have two opposite signs for helicity, one in the northern hemisphere and one in the southern hemisphere, but also two opposite signs for large and small scale structures. And he did a work based on SOLIS data where he more or less described this sign change of the sign change in helicity for different scales. The problem is that especially at the small scales there's not a very clear picture of what the helicity spectrum looks like. The important thing is that we need, again, to do this helicity spectra from, the best would be from data without height corrugation, so we want to do it on a geometrical height scale. And with sunrise we can do that for down to scales which were not accessible by other instruments so far. We achieved that by putting this 1 meter telescope into a gondola. The new sunrise gondola is displayed here. We have a completely new gondola built by APL. This gondola gives us much more stability than the first two flights because it has in addition also a roll compensation. We have 3 new instruments on board, completely new instruments. That is the chromospheric infrared spectropolarimeter from the Japanese colleagues, the UV spectropolarimeter built at MPS, and the tunable magnetograph built by the Spanish consortium. We have a significantly improved image stabilization system provided by the Kiepenheuer Institute in Freiburg, which allows us to achieve a stability of 0.01 arc seconds. And yeah, the payload is about 900 kilograms heavy, and the onboard data storage will be sufficient to store the data from our 5 to 6 days flight on 320 terabyte SSD disks. One quick image per instrument. So this is the these are the specs of the Japanese instrument, the Sunrise Chromospheric Infrared Spectropolarimeter. And the focus of this instrument is to observe the, it's a spectropolarimeter which observes in mainly these spectral regions here, the calcium infrared line, but also in the photospheric line, a potassium line which is blended from telluric lines and not accessible from the ground. The second instrument is this is how the instrument will look like, the SCIP instrument. It's already under fabrication. All the flight parts are more or less there and it will be assembled. The second instrument is the tunable magnetograph. It's similar to the already flown IMAX instrument, but it's a complete new, newly built instrument. And that's an imaging spectropolarimeter in two spectral lines. So we will observe, like in Sunrise 1, these photospheric iron lines, but we will also have a channel for the high photosphere, low chromosphere, using this magnesium 1B line. And the third instrument, which is built by us at the Max Planck Institute, is the Sunrise UV spectropolarimeter and imager. And there we will have the possibility to do this multi-line analysis. Just one slide about the current status and the timeline. All instruments and subsystems are now in hardware phase. The flight hardware fabrication has started and the mounting of everything has started. The telescope refurbishment is more or less done. All the parts have been inspected, and everything which was not working anymore, which was damaged from the second flight, is in manufacturing to be replaced. The mirrors are in good shape. The delivery of all instruments will happen end of this year, and then we have 1 full year time to first assemble the instruments at our institute. And the most important thing is, what we didn't have in the first 2 flights, we can do a proper test of the instruments by hanging the gondola out. We have a facility at MPS which allows us to really do already solar observations, of course with no seeing, but we will at least be able to track the sun, and we will be able to test all the instruments. And after this hang test at the MPS, we will do the thermal vacuum tests in our big MPS facilities. And yeah, in March 22, we pack everything, and then it goes for the launch, which will happen in June 2022. One slide showing the team we work with, that is led by us at MPS. Then we collaborate with Johns Hopkins University Applied Physics Laboratory in Maryland, USA. Then the Institute for Astrophysics in Spain, and the NEOJ in Japan. And of course also the Leibniz Institute in Germany. Yeah, and these are the names responsible for these instruments there, and we are looking forward to the launch in 2022 and to provide you with a high quality data set from the Sunrise 3 Observatory. Thank you.
People want to go to lunch? Oh, maybe we discuss during lunch. So let's thank Andreas once again. Durga.
Hi, so it's me again. We will have lunch outside. When you go, you have to cross the road and go through the campus on the other side. So you will see people going through that. A couple of announcements for, so there will be somebody at the desk outside. Our system did not let some people pay the registration fee because there was something wrong, something was going on. So if you have not paid a registration fee, now you can do that in cash. There will be somebody who will guide you to the account section. That can be done. People who have been given the TA, so please collect your form and attach all your tickets there. So you can again collect the forms outside and submit it to office number 103. On your badge here, you see there are 2 colors. So this one is orange, that's LOC, and other people have white. So if you have any questions or any concerns, just find people with this orange 5, right? Let's break for lunch now, and we'll be back by 2:30.